Hi there. You want to do some calculus with me for the next 2 hours or however long this is going to take? You do? Awesome. The AP Calculus exam is drawing near, and there's no better way to practice than to sit down and do an exam and feel what it's going to be like when the time comes. I'll put video chapters and timestamps in the description so you can skip around the video, but I would recommend watching this introduction just to set the stage here. The thing is, the College Board has only ever released 2 AP Calculus exams. The one we're doing today is from all the way back in 1988. Only once have they actually released an answer key, and that was to the 1988 exam. So don't gyp yourself out of the opportunity to do one of their official released exams. I'll put a link to this one in the description. You can download it and give it a try yourself. If nothing else, pause the video each time we get to a new question and try it out before watching me go through it. Even though this is so old, from 1988, the content, the questions, the wording, it's all pretty much the same, so this is great practice. The format of this exam is a little different from what they do today, but it's super minor. Let me tell you what the differences are now. Here are, by the way, the table of contents for this big document. They actually have, like I said, the answer key, but also some neat statistics too. So each time I do a question, I will put on screen if I got it right or wrong, and the percent of people who got it right when this exam was taken. So that should be fun. Let's go down to the intro where they tell us the format. We've got a multiple choice section consisting of 45 questions, and we've got an hour and a half to do that. And then a free response question consisting of 6 problems, hour and a half to do that. Now, from what I've read, when this exam was issued back in '88, graphing calculators were allowed for the whole thing, and that's the major difference between then and now. Here's the format of today's exam. It's the same amount of multiple choice questions, but you get a little bit more time, and it's split into a calculator and non-calculator section. The free response questions, just as many today, 6, and the same amount of time, and again, it's split into graphing calculator and non-graphing calculator. So the format's really similar, it's just a matter of the calculator that's the big difference. I'll try to minimize my use of a graphing calculator, of course. Going to try to go at a brisk pace and explain things at a level of detail that will hopefully be helpful for someone who's taken AP Calculus and is reviewing for the exam, since that is the target audience. Now, I'm just wrapping up my first year of teaching high school math. I teach AP Calculus and 4 other classes, so it's been a scramble to review this sort of material that I haven't done in years with all these classes, so I might bungle a question or two, but I think I'll do pretty good. Like I said, I'll put on screen if I got a question right or wrong, so you'll know if I just told you a bunch of nonsense. I've skimmed the questions on this exam. I haven't done any of them. I just skimmed them to see if it would be a good video. And so let's go ahead and get into it. Hopefully I get a 5. I will also, they have like scoring guidelines at the bottom of this document. So once I finish the exam, there'll probably be a cut, and I'll tell you what my score was. I'll go through the scoring process, but not on camera, because that would probably be really boring for you. There was one other thing I wanted to say, but I forgot what it was, so perhaps I'll remember it in a minute or two. Let's just get into it and see what happens here. Question 1. Start my timer. I got a stopwatch on my phone. I'm not super worried about the time, but, I'll watch it just out of curiosity. Question 1. Let's go. Y equals x squared times e to the x. We want to find dy dx. Classic, just derivative problem. We've got a product of functions, so we need to use the product rule. That's f prime g plus g prime f. Now, f prime is going to be 2x. F prime g is going to be 2x e to the x. And then g prime is going to be e to the x. G prime f is going to be e to the x squared. So that's our answer. We just got to match it with one of the multiple choice options. And it looks like it's this one, letter C, because we can factor out an x e to the x. If we factor out x e to the x, then this becomes 2 plus x. Yep, so C is the right answer. Moving on, I've also got a couple glasses of water here and a coffee, so I'll be sipping as we go through this. Question 2. What's the domain of the function given by this? Okay, we just got to check the denominator for problems, which is going to give us x can't equal 3 because we can't have 0. Check the square root. That's not going to give us any problems, right? Because actually, no, it will. Of course it will. We need x squared minus 4 to be at least 0. Can't have a root of a negative. And so that means x squared has to be at least 4. And so that means that x has to be at least plus or minus square root of 4. That's plus or minus 2. So, I mean, what that actually means is that x has to be 2 away from 0 or further. This notation is kind of sloppy. But that's the thing we're looking for. Absolute value of x has to be at least 2. But we also need to have that x is not equal to 3. Sorry, I wrote x equals 3. I was trying to say we can't have x equals 3. So we are looking for this one here. Absolute value of x is at least 2, and x is not equal to 3. What's the difference? Yeah, that one. For a second, I was like, what the heck is the difference between D and E? But E doesn't have the absolute value bars. It's fine if x is negative, right? Because like negative 3 squared, it's just going to be positive. So we need those absolute value bars there so that x is allowed to be negative 2. Yep, that's it. It's D. Question 3. A particle with velocity at any time t given by v of t equals e to the t. It's moving in a straight line. How far does the particle move from t equals 0 to t equals 2? So this is adding up rates of change. If we integrate velocity, we will get the position of the position of the particle. So we don't want to integrate velocity. We want to integrate the absolute value of velocity because we want to integrate the speed. If we integrate speed, we'll get the displacement. And that's what we're being asked about because we're asked how far does it move? Even if it, starts at 0 and ends at 0, it might have moved like, 10 meters or something. I think that's what the question is asking. So I got to integrate from 0 to 2. Now, of course, in this case, if I take the absolute value of the velocity function, the velocity function is e to the t. So that's always positive. So the absolute value isn't actually going to do anything, which is wonderful. So I'm just integrating e to the t from 0 to t. I think that's it, right? This is a velocity function. It's moving in a straight line. If I add up all the velocities, those rates of change, I'm going to get how much its position changed. And so this is an easy integral. The integral of e to the t is just e to the t. So I've got e to the t, and I've got to evaluate it from 0 to 2. Plug in 2, that's e to the 2 minus e to the 0, which is 1. And so it's A. All right, question 4. I need a sip of water. The thing with, filming long videos is that I've got to sit here in the bright, hot light with my lighting equipment, hunched over this desk. It's not the most comfortable position. The graph of y equals -5 over x minus 2 is concave downward for all values of x such that what? So what restriction do we need to put on x to guarantee that this graph is concave downward for all those values of x? Well, concave downward means the second derivative is negative. So let's take a look at the second derivative. First, we'll have to find y prime. Don't bust out the quotient rule here, by the way. That would be really silly. You might want to rewrite y as -5 multiplied by x minus 2 to the -1. And so now we'll take the derivative of that. And that's going to be +5 multiplied by x minus 2 to the power of -2. That's the derivative of y. It's just a simple power rule. And then take the derivative of that. Get my second derivative, and we can start to answer questions about concavity. It's just power rule again, -10 times x minus 2 to the power of -3. Now, for this to be concave downward, we need -10 times x minus 2 to the power of -3 to be less than 0. We need the second derivative to be negative. Okay, so divide everything by -10. That's going to give us that x minus 2 is greater than 0, because we divided by a negative, so you got to flip that inequality. And that was to the power of negative 3. Forgot to write that. To the power of negative 3. And then we can raise everything to the power of negative 1/3. Raise everything to the power of negative 1/3. That's going to give me x minus 2. But then if we raise to a negative power, we've got to flip the inequality. So then I get x minus 2. Oh, no. Can't do that. Can't do that because, we can't like involve an inverse, like a negative power, when I've got 0. That would be a silly thing to do. Okay. So if x minus 2 to the power of negative 3 is going to be greater than 0, well, I guess that's pretty easy, right? That means that 1 over x minus 2 cubed is greater than 0, and so x just has to be greater than 2. Yeah, if x is greater than 2, then the denominator is going to be positive and will be good. So that's going to be option E, which is slightly cut off. That's got to be what's supposed to be there. X is greater than 2. Letter E. All right. Moving on to question 5. Let me take a sip of my coffee and hopefully not burn my tongue. We're almost 10 minutes in. Okay, it's not that hot, so I won't drink so slowly next time. Okay, 5, easy, it's tangent. The integral of secant squared is tangent of x plus c. You got to know that one. That's letter A. All right, number 6. If y equals ln x over x, then find the derivative of y. We got a function divided by a function, so make sure that there's no nice simplification you can do, and if there's not, go ahead and use the quotient rule. Quotient rule is f prime g minus g prime f all over g squared, or as that yodeling song goes, what is it? It's high d low, high d low minus high. I have no idea what that song is. High d low minus low d high. I don't know. F prime is 1 over x, right? That's the derivative of ln x. And then it's f prime g. G is x, the thing in the denominator, minus g prime. G prime is 1 because g is x. G prime f, okay, so that's g times the natural log of x. Don't forget to divide by g squared. And what have we got, folks? It's 1 over x times x. That's 1 last time I checked, minus the natural log of x all divided by x. Where is that? I don't... Oh, it's x squared. Okay. I was getting nervous. I was like, man, that's not good. 1 minus ln x over x squared. All right, next one. 7. Oh, geez, Aloo. Oh, for a second, I thought we were going to have to do completing the square, which is fine, but I don't know how well I would explain it. This is just u sub. It's u sub because, look at this guy in the square root. If we take his derivative, we're going to get 6x. And, with u sub, what we're looking for is a coefficient, or let me put it differently. We're looking for a constant multiple of the derivative of u. The derivative of u, if I let u be 3x squared plus 5, the derivative is 6x. And I've got a multiple of that up in the numerator, so that's going to be great. All right, u sub, let u equal 3x squared plus 5. Take the derivative, du is equal to 6x dx. And I want to turn, I just want to get x dx on one side so that I can do the substitution. So I'm going to divide both sides by 6. That gives me 1/6 du equals x dx. Now I can go ahead and rewrite the integral. I'll write it down here. X dx, that gets replaced with 1/6 du. And I'm just going to bring the 1/6 out. Put my du there. And what we're left with is 1 over the square root of u. You want to rewrite this as a power because, that makes everything easier. It's u to the power of negative half du. And so this is just power rule. I've got to bump up the exponent by 1. So that's going to give us u to the 1/2. Just add 1 to the exponent, but then divide by the exponent. So we divide by 1/2, which is the same as multiplying by 2. So 1/6 becomes 2/6. And this becomes 1/3. Just plug our expression for u back in. We set u equal to 3x squared plus 5. So 3x squared plus 5 to the power of 1/2 and, plus c. I'm being a little flippant with the plus c. I'm just going to put them on at the end. Okay, where is our answer? 1/3 3x squared plus 5 to the 1/2 plus c. Wonderful. All right. The thing I was going to say earlier, by the way, answer's D, we're done, was that the video will probably cut at some point when my camera's like about to die or filling up on storage space. It's got 2 bars of battery right now, so, I'll go as long as I can. I'll have to switch out the batteries at some point, though. Question 8. The graph of y equals f of x is shown in the figure above. On which of the following intervals are... Oh, I was like, why are they using a plural when they're only asking about one thing? We want to find where the derivative is positive and it's concave down. Second derivative is negative. Concave down is going to be like, well, let me use my highlighter. Concave down is right there, and then we need the derivative to be positive. And the derivative, we're talking about the slopes of the tangent lines. So these guys, they got to be positive. So that would be between B and C. The derivatives are positive here. It's, the slope is positive, and it's concave down. So from B to C. B to C right there, answer 2. That's it. Yeah, is that it? That's it. That's it for sure. Letter B. Let me get my highlighter. It's letter B. All right. Question 9. If x plus 2xy, this looks like implicit differentiation. If x plus 2xy minus y squared equals 2, then at the point 1, 1, dy dx is what? Okay, we just got to do implicit differentiation and then plug in the point 1, 1. So for implicit differentiation, we'll differentiate both sides with respect to x. X becomes 1, and then this is a product rule. Don't screw that up. I'll say the first function is 2x. The second function is y, which is an implicit function of x. So f prime, the derivative of 2x, is 2. F prime g is 2y plus g prime f. G prime is our dy dx, and then f is just 2x. And then here we've got chain rule with the minus y squared. I've got to take the derivative, the nice simple minus 2y, but y is a function of x. So we also have to multiply by dy dx. And this equals 0 on the other side because we're differentiating. Okay, let me move this. I'll shrink it a little bit so I've got some room. And just collect my dy dx terms and move the other junk to the right side. So I'm going to say dy dx, and then in parentheses I'll put the factors. So I've got a 2x needs to be there, and a minus 2y needs to be there. And then on the right side of the equation, minus 1, minus 2y, just subtracting those things over. And so we have that dy dx equals, I'm just dividing both sides by 2x minus 2y, so this becomes 1 minus 2y, divide by 2x minus 2, oh no. The answer is E. Okay, wonderful, right? Because the denominator, it's 2x, 2y, but the point we're asked to plug in is 1, 1, so yeah, divide by 0. We ain't doing that. That's non-existent. All right, we're 15 minutes in. We're on question 10. That's good. Let me take a sip of water. I've got my E glass here. I don't know if you can see that, but it's an E glass, the number E. Okay, here's a cool problem. We got the integral of 2kx minus x squared. We're told that this definite integral from 0 to k equals 18. We just have to solve for k. So, don't worry about how you're going to figure it out. Just do the integration. It'll all be okay. We're integrating with respect to x. K here, that's probably the important thing to notice, is that k is a constant, okay? So let's go ahead and do this. 2kx, if I integrate that with respect to x, it's going to become kx squared, right? If I were to differentiate this, the 2 would come down, and there's a 2 there, so I don't really have to do anything else. It's just kx squared. And then minus a third x cubed. Now this would be evaluated from 0 to k, and I know it equals 18. I'm told that. So Now we just got to plug the stuff in and solve. Plugging in k is going to give us k cubed minus a third k cubed. And then plugging in 0 would just give us zeros. So we have that this equals 18. Nice. And so this means that 2/3 k cubed equals 18. I don't see any ugly answers, so hopefully the fractions here work out nicely. I'll divide 18 by 2/3, okay? So I've got k cubed equals 18 divide by 2/3, which means multiply by 3/2. Ah, yeah, beautiful. 18 over 2 is 9, and then multiply by 3 is 27. K cubed equals 27, which means k has got to be positive 3. Positive 3. For a second, I was afraid I didn't see it there. Positive 3. That's letter C. All right. Question 11. Oh, it's finding a tangent to a graph. Easy. Take a quick sip of coffee here. Man, it's such a big drink hole in this thing. It's not practical. It's not right. It's all wet on the desk. Oh, what a mess. Okay, how much battery I got? Enough. Question 11. An equation of the line tangent to the graph of this function at the point 1, -1. What do you need for a tangent line? You need a point, you need a slope. Easy. I got a point. To find the slope, you need the derivative. That's the whole idea, right? F prime of x, then, we'll find the derivative. We're going to have to use a product rule because we've got x times 1 minus 2x cubed. Unless you want to expand that, but I'm definitely not in the mood. So let's do product rule. F prime g. F prime is 1, so f prime g is just 1 minus 2x all cubed. And then plus g prime f. F is x, so I'm just going to put the x there and then worry about g prime. Got to differentiate this. It's going to be chain rule. So I'm going to get 3 times 1 minus 2x to the power of 2. And then I need the derivative of the inside thing. So multiply by -2. And what are we doing here? Finding the slope, right? Okay. So you could, try to simplify this a little bit. There's really no point, right? I mean, I'm just going to plug in x equals 1 and get my slope. So let's see. If we plug in x equals 1, this is going to be 1 minus 2, which is -1, cubed is -1. I'll try to be careful here. I wouldn't want to screw this up and lose a point just for this. Plug in 1 here, that's just 1, so I don't care. 1 minus 2 is -1, squared is 1, so 3 times -2, so -6. -1 plus -6, so -7. And yeah, I don't even have to make the line anymore. It's right there. Obviously, if I wanted to be super careful, I could plug it in and just make sure that I am getting one of these answers. But if I got a slope of -7, it's got to be answer A. So moving on. If f of x equals sine x, then f prime of pi over 3, well, f prime is just cosine, right? Because the derivative of sine is cosine. So what is cosine of pi over 3? I can struggle with my unit circle, honestly. It always takes me some time to recall. But I always think of it like this. Think about that first quadrant. And if I were to fill it in, I know that x is cosine and y is sine. And I just kind of fill it in like this. 1, 2, 3. I know that all of these things are divided by 2 and that I need to take square roots of them all. And of course, the square root of 1 is just 1. And this is the guy we're looking for, pi over 3. Cosine, it's 1/2. Answer B. Again, f prime here is cosine because f is sine. All right. Still got a couple bars of battery, so we'll keep on going. Question 13. If the function f has a continuous derivative on this closed interval, then the integral of f prime from 0 to c equals what? Well, that would just be in here we've got f prime. So if I integrate it, I'm just going to get f of x. And then I need to evaluate it from 0 to c. So I'm going to get f of c minus f of 0. F of c minus f of 0. And that's right there. Yup, that's it. Okay. Question 14. what's going on here? This is u sub. It's u sub, right? Because if you let u equal 1 plus sine, derivative of sine is cosine, and it's all gravy. I wish I didn't have to, do it. I wish I could just stop there. It's going to be easy. Let u be 1 plus sine theta. Take the derivative of both sides. So du is cosine theta, d theta. And hey, look, now we can immediately do the substitution. I've got the cosine theta, d theta, in the integral, and I know that cosine theta, d theta is du. So we're doing change of variables here. This integral, what's inside? It's 1 over the square root of u. So u to the negative half. The cosine theta, d theta, is getting replaced with du. And then let's change the bounds to put them in terms of u. If theta is 0, then u is 1 plus sine of 0, which is just 1. And if u is pi over 2, if theta is pi over 2, then u is 1 plus sine of pi over 2, which is 1 plus 1, and so that's 2. And we already did this integral earlier. It's going to be 2 times u to the 1/2. Yeah, increase the power by 1 and then divide by that power. You divide by half. That's the same as multiplying by 2. And we are evaluating this from 1 to 2. So this becomes 2 times the square root of 2 minus, the square root of 1 times 2, which is just 2. And it looks like they're factoring a 2 out of this to get an answer of 2 times root 2 minus 1. And that's letter D, 2 times root 2 minus 1. Nice. It's funny, an integrand like this, it's really easy to look at that and be like, oh no, trig and a square root, but man, u sub really cleans up nicely. Okay. Question 15. I think after this, we'll be a third of the way done. All right. Hey, this is easy. Take the derivative and plug in 2. The function is square root of 2x. So this is just a simple chain rule. F of x, you want to, when you see these roots, okay, you should probably rewrite them as powers. In most situations, that's going to be helpful. Not all the time, but in a lot of situations, that's going to be helpful. So if I rewrite this as a power, it's 2x to the 1/2. Clearly, I just got to use a chain rule to find the derivative, f prime. That's going to be 1/2 times 2x to the minus 1/2. I'm just doing the power rule on the outside function. Multiply by the derivative of the inside function. And so this is just let me write it like this. It's 1 over the square root of 2x, right? Because it's just, the 2, the 1/2 cancel out, so that's it. And then I got to plug in a 2. And if we plug in 2, we get 2 in the denominator because square root of 4. So 1/2. B. All right. 16. Let me try taking a sip of this coffee without getting it all over myself. Yeah. Hits the spot. A particle moves along the x-axis so that at any time t greater than or equal to 0, its position is given by this. That's our position function. For what values of t is the particle at rest? So it's going to be at rest when its velocity is 0. Velocity is the derivative of the position function. So take the derivative and basically find the critical points, right? Set it equal to 0 and all that. Okay, so v of t, the velocity function, it's the derivative of the position function, and that's going to be just a bunch of power rule. So 3t squared minus 6t minus 9, and this is a quadratic that we need to solve, figure out when it equals 0. Let's go ahead and try to factor. If I'm going to factor this, I know that I'm going to need a 3t and a t so that we get the 3t squared. And we're going to need some things that multiply to negative 9, so probably a minus 3 and a plus 3. Is that going to work? That would give us 9t. That's not going to work. 9t minus 3t. Nope. Okay, so then should we do, flip the signs, right? Make this a plus, make this a minus. Then we're going to get a plus 3t and a minus 9t, so minus 6t, and everything else is going to work out. Beautiful. So that's the factorization. Set it equal to 0. Thus, solving this one. If this one is equal to 0, then t is going to have to equal -1. If this one is equal to 0, t is going to have to equal 3. So I've got -1 and +3. That's not good, because that doesn't agree with any of these. Oh, hey, we're all good, right? T is positive, of course, so that's an extraneous solution. T equals 3. T equals 3 is what we're looking for. 3 only. Okay. Yeah, that's why it's always important to read the question, right? T is greater than or equal to 0. Of course it is. It's time. It's positive, or at least non-negative. All right, question 17, quick definite integral. Integral of 3x minus 2 squared from 0 to 1 might look a little scary at first, like, oh, how do I integrate this? You could use u sub, but since the inside function is linear, it's pretty easy to get by without using u sub, which is what I'm going to do. So I'm just going to apply the power rule, right, which is going to give me 3x minus 2 squared, cubed, and divide by that new exponent. So if I were to take the derivative of this, what's going to happen? Well, the 3 and the third are going to cancel out. The power of 3 is going to become a power of 2, which is good. The only other thing is that the chain rule is going to give me an extra factor of 3. And so I actually need to divide by another 3. So this should be 1 over 9. And then I got to evaluate from 0 to 1. So, you just got to check. If you take the derivative of your integral, make sure that you get what you're supposed to, and if not, you can adjust it accordingly. And thinking about it like that, you can avoid using u sub in a pretty simple situation like this. All right, so if I plug in 1 here, well, let me just take the 1/9 out. If I plug in 1, I'm going to get 3 minus 2, which is 1 cubed, and that's just 1. If I plug in 0, I'm going to get -2 cubed, which is -8. So that's going to become +8. Hey, it's 1. 1/9 of 9 is 1. And there it is, letter D. All right, question 18. So far, so good. Let me take another sip of water here. I lose my voice easily, so I might have to keep on, drinking a lot. What do we got going on here? Oh, just a second derivative. So this is why it's 2 cosine of x over 2. Oh man, I hope they don't require me to use a trig identity on any of these problems. I'll probably forget if they do. Unless it's Pythagorean. If it's Pythagorean, I'm good. But anything else, I don't know. We need the second derivative. Don't be, intimidated by the notation. That is second derivative. So how will I write this? Well, let's just do y prime down here. Pretty simple, just chain rule. The derivative of cosine is negative sine. So this is going to become -2 sine of x over 2. Then you got to multiply by the inside function, the inside function's derivative, The derivative of the inside function is 1/2, which will actually cancel out with that 2. So I'm just going to erase the 2. So we've got negative sine of x over 2, but we need the second derivative, so I'm going to just differentiate this again. Derivative of sine is cosine. Chain rule is going to give me a 1/2, so -1/2 cosine of x over 2. And that's right there, letter E, -1/2 cosine x over 2. We're cruising. Question 19, definite integral, u sub. This is u sub, right? Let u equal x squared plus 1. And the derivative of that is 2x. And hey, we got a multiple of 2x in the numerator. We're going to be good to use u sub here. These integrals can look kind of scary when you get those polynomials in the denominator, but have no fear, u sub is here. U equals x squared plus 1, take the derivative, du is 2x dx. If du is 2x dx, divide both sides by 2 to find that half du is 1x dx. Now I'll do the substitution. I know that x dx is half du, so I'll rewrite the integral as 1 over u, right? 1 over u, which is the same as, I'll just write it like that. 1 over u, and then du, because x dx gets replaced with half du. Don't forget the half, but let me pull the half out. Then we just want to rewrite our bounds. If x is 2, then u is 5, so the lower bound is 5. I'm trying to hit my undo button here. There we go. The lower bound is 5. If x is 3, then u is 10, so the upper bound is 10. And so this is equal to, I'm getting a little scared looking at these answers. I'm like, I got 2's in there. I'm sure it'll work out. So this is going to be 1/2, integrate 1 over u to get natural log of u. And we're going from 5 to 10, so I got to evaluate from 5 to 10. This is going to equal then 1/2 times, yeah, I see it. Easy, easy. Just got to know your log rules. 1/2 natural log of u, let me plug in the 10, minus the natural log of 5, and this is going to be 1/2 natural log of a difference of logs is the log of the quotient. So, 10 over 5, I can bring that into a single log. And 10 over 5 is 2, so this is 1/2 ln of 2, which is letter B. I had a quick pro tip I wanted to give you. If you don't remember your log rules, just plug this into a calculator and check it against the answers, and you'd be fine. All right, question 2. This one looks a little long. Let me take another sip of water. We're looking at just over 30 minutes. I think we're making fine time. Let f be a polynomial function with degree greater than 2. If a is not equal to b and f of a equals f of b equals 1, so I just draw a quick picture here. It's a polynomial function with degree greater than 2. It's greater than 2, and at 2 different points, a not equal to b, at 2 different points, it comes up and hits the y equals 1 line. Which of the following must be true for at least one value of x between a and b? The function is 0. Nope, that doesn't have to be true, right? Because our function could just look like this, right? It could come down, hit 1, and turn around and hit 1 again. It doesn't have to go all the way down to 0. I know its degree is greater than 2, but it could still look like that. F prime is equal to 0. Does that have to be true? Yes, I believe so, because it's going to have to, pass through y equals 1 in one direction. It could be going down to do it and then going up to do it, or it could be going up and then down, but it does have to change direction in order to hit y equals 1 twice. And so option 2 is true. The derivative is going to have to be 0 at some point between a and b. A and b are right here, by the way. So obviously drawing a picture is a useful strategy here. Option 3 is that the second derivative has to be 0. No, the second derivative is the concavity, so it could very well just be positive this whole entire time. So 2 only, letter C. All right. Question 21. The area of the region. We got an integral problem. Let me switch to a red marker just for kicks. The area of the region enclosed by the graphs of y equals x and y equals x squared minus 3x plus 3. Hey, another fun problem to just crack out a graph real quick, just to get a good idea of what we're looking at. Of course, you could do this on a calculator, but I'll just sketch it because this is pretty simple function stuff. If y equals x, that looks something like that. X squared minus 3x plus 3. The vertex, the x-coordinate of the vertex of a quadratic equation is negative b over 2a. So that's 3 over 2a, so 3 over 2. So, we're maybe like right over here. And this is an upward-facing parabola that's been shifted up 3. So, my scale might be off a little bit, but it must look like this. It must look something like this then, for sure. And so the region is in there. It's right in there. So let's set up the integral then. We got to see where these guys intersect so that we know what the bounds of the integral should be. So let's go ahead and find those. But for starters, we see that y equals x is the top function. So just to set this up, it's going to be x minus the bottom function, and the bottom function is x squared minus 3x plus 3 dx. You could find that the line is the top function by plugging in a value. Let's just figure out where they intersect first, and then we can do that just to show you that for sure the line is the top function. So if y equals x, then we have that x equals x squared minus 3x plus 3. Just plugging this into this. And so that means that, I'll go on to another line, that means that x squared minus 4x plus 3 has to equal 0. And good thing we can factor this. I really don't want to use the quadratic formula. X minus 3, x minus 1, that's good. So x has to go from 1 to 3. Now, if we plug in 2, just a number in this interval, if we plug in 2, we'll see that y equals x is greater than this guy. So if you plug in 2, this guy obviously is 2, but this one is 4 minus 6. Why did I write 2? 4 minus 6 plus 3. So that's 1, right? That's 1. So like I said, the line is the top function. Okay, what was the question? We got to do the integral, right? Do the integral. Okay, this is easy now. The integral is just power rule. I guess I'll go ahead and zoom in here. So this is going to become 1/2. Let's just simplify the expression first, right? So it's the integral from 1 to 3 of, I'm going to take out a factor of -1. Take out the factor of -1, and this is going to be x squared plus, not plus, minus 3x, but plus that x, so minus 2x, just to show you what happened there, right? There's a minus here, there's a minus there, so it should be plus 3x, but I took out a negative, so it should be minus 3x, but this x is positive. Wait, so then should it be minus, you know what? Forget taking out a negative. Let's just do this a slow and steady way. I don't want to make some dumb mistake. Negative x squared, this is positive x plus 3x. So that's going to be 4x and then minus 3 dx. All right, and this is equal to, let's just bust out the power rule. It's going to be -3 x cubed plus 2x squared minus 3x. I'm going to have to just move this to another line because I'm running out of space, and evaluate this from 1 to 3. If we evaluate this from 1 to 3, we're going to have -1/3 times 27. I'm plugging in 3 right now. Plus 2 times 9 is 18, minus 3 times 3 is 9, and then we have to subtract plugging in 1. If we plug in 1, we get -3 plus 2 times 1, so plus 2, and then minus 3. I sure hope we get the right answer here. -3 of 27 is -9. 18 minus 9 is positive 9. Hey, so that's just 0. And then we just have minus all of this junk. So positive 3rd minus 2 plus 3. So minus 2 plus 3 is plus 1. So 1/3 plus 1. So 4/3. Let's see, is 4/3 an answer? Yes, it is. Letter C. Let's go. That's right. For sure. All right, what do we got next? What's my battery looking like? Looking good. We are 40 minutes in. If natural log of x minus natural log of 1 over x equals 2, then what does x have to equal? Bust out the log rules here, right? So since we have a difference of logs, we can write that as the natural log of the quotient. So ln of x divided by 1 over x. Dividing by 1 over x, though, is multiplying by x. So this is actually ln of x squared that equals 2. And then if we have a power inside, we can take that out as a factor. So yeah, really got to know your log rules here. 2 ln of x then equals 2. So ln of x has to equal 1. And so that's going to be e, right? You got to raise e to a power of 1 to get e. And so the answer is C. Bam. All right, question 23. Let me take another sip of my water. I got one sip left in that glass. L'Hopital's question, I think. If f prime is cosine and g prime is 1 for all x, and if f of 0 is g of 0 is 0, we want to evaluate the limit of f of x over g of x. To use L'Hopital's rule, with a limit, you got to have an indeterminate form if you were to plug in the number we're approaching. We're approaching 0, and if you plug in 0, you get 0 over 0, because it tells us the functions are both 0 at that point. So we've got an indeterminate form. We can use L'Hopital's rule and just evaluate the limit of the quotient of the derivatives instead. So this would actually become, by L'Hopital's rule, the limit as x approaches 0 of, that's a really bad fraction bar, but we're going to go with it, cosine of x, the derivative of the numerator, which was given to us, over g prime of x, which is 1, the derivative of the denominator, also given to us. Now we can plug in 0. Cosine of 0 is 1, so this is just 1, and the answer is B. 24. Find the derivative of x to the natural log of x. Find the derivative of x to the natural log of x. What the heck? Is this going to be a... Yeah, that's a weird problem. This could be a, what do they call it, logarithmic differentiation. Like, so we could say let y equal x to the natural log of x. That does not have the all right. Oh, sorry. I'm confused because I wrote it wrong just a minute ago. It's supposed to be x to the ln x. I wrote it as multiplication. Sorry. Yeah. So now we take the natural log of both sides. So I said, hey, let's call this y. That's our function. And I want to take the log of both sides because taking the natural log can turn a power into a factor, which makes things easier. So this is the natural log of y equals the natural log of x to the ln x. But when you've got a log, a power inside is the same as a factor outside. So this becomes the natural log of y equals the natural log of x times the natural log of x, bringing that power out as a factor. And so now this is just going to be product rule, right? Because we've got natural log of y equals the natural log of x squared. And we're looking for the derivative, so now we can just differentiate, and then we're going to just solve for dy dx. Remember, we're looking for the derivative of x to the ln x, and y is x to the ln x. So if we can find dy dx, we'll be good. Take the derivative of both sides, so the derivative of natural log of y becomes 1 over y, but y is a function of x, so I've also got to put in here dy dx. Of course, we don't know what this guy is. That's the whole crux of the problem. And this equals the derivative of this, which is going to be 2 times ln x. That's just power rule, but then you got to multiply by the derivative of the inside function, so 1 over x. Man, what a mess. Then we're going to multiply both sides by y to solve for dy dx. But before I do that, remember y is x to the ln x. So I'm just going to write it that way. It's x to the ln x, that's multiplying by y. Oh my god, I did it again. What? I wrote x times ln x. Remember, it's supposed to be x to the ln x, right? That's what y is. It's x to the ln x. Man, I can't believe I screwed that up twice. So this should be x to the ln x. How's that going to change things? Now we can't cancel that x with that x. So what's going to happen is, well, by exponent rules, this would become x to the ln x minus 1. But it doesn't look like they wrote it that way because I see a 2 over x there. I see an x in the denominator in one of the answers. So I'm going to keep x in my denominator and write this as 2x to the ln x times ln x. Is that the answer? 2 over x, ln x, x to the ln x. Yep, that's it. It's C. If you look at it, my answer here matches C. So that's this cool thing, logarithmic differentiation. I don't think it's on the curriculum for AP Calc anymore, or, if it is, it's very sneaky. So, yeah, that's how you do it. You might want to look up a video on that if it's new to you. I'm not going to go through it again because my voice, I need more water. Here we go, question 25. I think explaining all of these is making this take longer than I had expected. Okay, for all x greater than 1, if f of x equals the integral of 1 over t from 1 to x, then what is f prime? Okay, so we just got to take the derivative of this integral. So it's basically fundamental theorem of calculus. Now, the fundamental theorem of calculus tells me that if I take the derivative of the integral, right, the integral is f of x. So if I take the derivative of this, I should just have 1 over t. But if I remember how this works, how does this work? You have to multiply by the, oh no. How does this work? 1 over t, is it just going to be 1 over x? Something's telling me I got to multiply by an x, which would make this 1. The integral goes away because we take the derivative. So, yeah, if we were to integrate 1 over t with respect to t, it would become natural log of t, and then I would plug in an x. It's 1 over x. I'm pretty positive it's just 1 over x. What I was just going through in my head is if we actually just integrate this, just integrate 1 over t with respect to t with these bounds, and you're going to get natural log of 1 is 0, so you really just get natural log of x. And if you take the derivative of that, which is what we're asked to do, then you would just get 1 over x. So the answer is B. 26, integral of x cosine x dx. From 0 to pi over 2. What the heck? That's weird. So this, we could do this with integration by parts, but this is a Calc AB exam, and integration by parts is not covered on AB. But I don't really want to put this into a calculator, which I guess is what you would do if you were doing this on AB. So let's do integration by parts real quick. I'm going to use parts because I notice there isn't another way to do it, is there? I don't think so. I notice that I've got a function whose derivative is going to get nice and simple, so parts will work. I'm going to let u then equal integral uv. I'm just trying to remember it. Parts is uv minus the integral of, okay, this is fine. I'll let u equal x, and so then du equals dx. Now for v, if you remember how parts works, which maybe you don't, maybe you do, you're actually going to pick dv. dv is going to be what's left, cosine x dx, and then I can integrate this to get v, and the integral of cosine is sine, so I get just sine of x. Okay, and then the parts formula is that this is equal to uv with, whatever the bounds are, and in this case, uv is x sine of x, so x sine of x from 0 to pi over 2, uv minus, it's minus the integral of v du. So v, which is sine of x, du is dx, nice and easy, and the bounds are from 0 to pi over 2. All right, this becomes the 0 here, if we evaluate this at 0, it's just going to be 0, so that's fine. If you plug in pi over 2, sine of pi over 2 is 1, and so you would just have pi over 2 from the x. So we're done with that. The integral of sine is negative cosine, but we have a negative out here, so those will cancel out, and it's just plus. Plus cosine from 0 to pi over 2, and I'll just continue it down here. This is going to be pi over 2 plus cosine of pi over 2 is 0, and then minus cosine of 0. Cosine of 0 is 1, so that's minus 1. So it's just pi over 2 minus 1, which is letter E. All right, my camera is on its last bar of battery, so I'll just take a pause here and have a sip of water, quick bathroom break, and we'll be right back. All right, I refilled my water. I switched out my camera battery. My SD card might fill up, so we might have to stop again for that. Narrating all of this, it's taken a little longer than I expected. It's 5:16 now, so let's keep on going. I gotta get dinner. And try to speed it up a little bit. We're on to question 27. Here we go. This one looks not so bad. At x equals 3, the function given by, we got this piecewise function, is, well, what is it? At x equals 3. So really what we want to do for starters, let's just plug in 3 to see if what we got going on the left is the same as what we have going on the right. X squared is continuous, and if we plug in 3 at x squared, we get 9. So this piecewise function will be approaching 9 from the left. From the right, it will also be approaching 9, because if you plug in 3, you get 18 minus 9. Okay, so from the left and from the right, we're approaching 9, so that's good. It also equals 9. If you plug in 3, here, it's actually equal to 9. So it is continuous. Differentiable but not continuous, that can't be the answer. Continuous but not differentiable, or both continuous and differentiable. Those are the two options. So we just have to consider the slope of the left side against the slope of the right side. If they're the same, then we should be good. The slope of the left side is going to be 2x, and at x equals 3, that's going to give us a slope of 6. For this guy, the slope is just 6. So yeah, I think we're good. This guy is differentiable because, the slopes match up, so it's not like some sudden non-differentiable jump in slopes. The slope is 6. From the left, from the right, we're good to go. It is continuous and differentiable at x equals 3. The limits line up, the slopes line up, we're good. 28. The absolute value of x minus 3 from 1 to 4. X minus 3. So you could deal with the absolute value if you want, split up the integral. I'm going to turn this into a geometry problem, because why not? X minus 3 in an absolute value bars, it looks like this, basically, except no. No, because it's x minus 3, so it's been shifted over to the right 3 units. Yeah. Absolute value, but shifted over to the right 3 units. If I plug in x equals 3, I get 0. So what am I doing? Why am I writing it below the x-axis? It looks like this. Looks like that. So the integral of this guy from 1 to 4 is going to be like these two right triangles. This one here and that one there. Sorry, I was sketching it wrong there. It's just been shifted over to the right 3 because it's absolute value of x minus 3. So just a couple right triangles. The integral, which is the area of these right triangles, it's going to be 1/2 base times height. The base of this guy is 2, and the height is, well, just plug 1 in. What do you get? 1 minus 3 is -2. Absolute value of that is 2. So there we go. Add in the area of this right triangle. And that's going to be 1/2. The base length here is just 1 because it's going from 3 to 4. So the base is just 1. And the height is plug in 4 to find out. 4 minus 3 is 1. Absolute value is 1. So that's just going to be a 1 there. 2 times 2 is 4, times a half is 2, plus a half is 2.5. 2.5, so 5 over 2. That's letter C. All right, use geometry. You could split up the integral if you want. Integrate from here to there and integrate from there to there. I like geometry, though. Absolute value, triangles, not so bad. 29. Yeah, here's a tricky one, right? This is a hideous limit, but the idea here is that although the limit looks really ugly, it's actually just the limit definition of the derivative. So you just have to know how to take a derivative. So we've got tangent of 3x plus h times tangent or minus tangent of 3x. So our function is tangent of 3x, and the limit is saying, hey, let's have h approach 0, and we've got an input of x plus h. We're subtracting an input of x. This is just the derivative of tangent of 3x. That's all it is. You got to recognize that limit definition of the derivative. So if I take the derivative of tangent of 3x with respect to x, that's going to be secant squared of 3x, but the chain rule is going to give us a factor of 3 in front. So 3 secant squared of 3x. Letter B, I need more coffee. I need a Werther's original or maybe a cough drop too, but can't get over how big the hole on this thing is. I've not really used this mug before. Okay, 30. Oh boy, what's this? Volume. A region in the first quadrant is enclosed by the graphs of y equals e to the 2x. Let me start getting a graph set up here. Could always bust out the graphing calculator if we want, but again, I said I'd try to minimize calculator use. E to the 2x is going to look something like that, and x equals 1 is going to look something like this. Just make it a dotted line, just to distinguish it from the y-axis. We got a region enclosed, so that's this character there. And it's rotated about the y-axis, okay? The volume of the solid that is generated is represented by which of the following integrals? So if this guy, it's rotated about the y-axis, we got to think about what the cross-sections are going to be. It's a little weird to me just because it's rotating about the y-axis, but the bottom of it is flush with the y-axis. So I'm just having a little bit of trouble picturing it. It's kind of like, I don't really know how to describe it. It's got these triangle edges, but it's like caving in at the middle. It's caving in at the middle. That's a strange thing, because if we rotate it about the y-axis, it's gonna look something like that. And so what's the volume of this solid? Well, I guess, it's going to be symmetric, so I'm thinking we could hit it with a factor of 2 and just worry about half of the solid, because half of the solid, it's revolving around the y-axis. Half of the solid will be a semicircle, right? So then we just have to double that. Okay, I think that'll work. So I've got to think about what the radius of the semicircular cross sections are gonna be. And if I sort of zoom in on this picture, I shouldn't be drawing it like a triangle, right? It's looking more like this, looking more like that. But if I take just a horizontal slice of the solid, that is going to give me a semicircle, because the thing has been, it's rotated around the y-axis. So if I take a horizontal, but is it going to be a semicircle? No. It's a washer problem, right? Isn't it a washer problem? Because this function, the line x equals 2, this line here, that's going to be like giving us a cylinder, but part of the cylinder is going to be getting cut out by the e to the 2x. So yeah, I think this should be like a subtraction thing with the washer method. My only hesitancy there is that I don't see any subtraction, and so I'm like, could it be the washer method? Could it be the washer method? If we're rotating around y, then we should be integrating with respect to y. So I'm starting to look at these two characters. Natural log squared, that kind of looks like a radius squared type of thing. Pi over 4, that could come from, where would a pi over 4 come from? I'm not sure. It's a tricky problem. Maybe I'll come back to this one. My hesitant answer, it's got to be with respect to y, because we're revolving about the y-axis. And so, in general, I'd get these circular cross-sections. It's just the fact that, we don't actually have a circle because there's nothing there right in the middle. And for a second, I thought those were going to be semicircles, but they're not going to be semicircles. Like if we take a cross-section of one half of this solid, it's going to look like that. So I don't know. Maybe I could figure this out if we just do it like this. And this guy on the outside is getting traced with the revolution by x equals 2. So if I'm trying to set up this integral, I'm going to say that I need half of the circle traced out by it's got a radius of 2 because, it's getting traced out by x equals 2. So this distance is 2. So it's half, pi r squared, and r squared is 4. And then I need to subtract half of what's getting traced out by the inner curve, which is e to the 2x. So half pi r squared. R is the distance from the y-axis to the function. And that distance depends on y. So we need to put this in terms of y. So if y equals e to the... I know my explanation here is not good, I'm just trying to sort the problem out. Take the natural log of both sides. ln of y equals 2x. Divide both sides by 2. X equals ln y over 2. So I can see where a fourth is going to come out here probably. So that's going to be my radius, ln y over 2. And then that's got to be squared. So divide by 4. ln squared of y. That thing is giving me the radius that's the radius of the circle that's kind of being traced out by e to the 2x here. That's what that is giving me. And it's a function of y because the radius depends on what y I am at. So I think the integral should be the integral from 0 to... I'm going to say e, because when do these things intersect? Whoops, I'm erasing. When do these things intersect? Well, x is 1, what? If x equals 1, then they would intersect... Oh yeah, obviously it's got to go from 0 to 1, right? It's got to go from 0 to 1 because that's the whole thing, x equals 1. But all the 0 to 1... all the 0 to 1 integrals are like this, they're in terms of x. And I'm thinking that we should be going with respect to y, because we're taking like these sort of semicircular little cross sections. So I want to... Oh yeah, right. So I want to go from 0 to... to e. But I want to go from 0 to e squared. That's my problem here. If I look at these things, take out a half, I could take out 2 factors of a half if I wanted to, and I could take out a pi. That would make this pi over 4, and then I would have 2 minus ln squared of y over 2. That's obviously not working out here. Okay, so I know I could figure this out. I think we've got to go in terms of x, because these guys, their bounds are not right. If we're going to go with respect to y, it's got to be from 0 to e to the 2, and that's not what's going on here. So yeah, I'm not sure. I'm going to have to move on. Skip 30. I don't like 30. Can't spend all day on that. If f of x equals x over x plus 1, then the inverse function f inverse is given by what? We'll just call this y equals x over x plus 1, and then we've got to solve for x. Doing that is going to give me, well, let's multiply both sides by x plus 1. So x plus 1 multiplied by y equals x. And then we've got that xy plus y equals x, but I'll just go ahead and subtract x from both sides. So minus x equals 0. And then subtract y from both sides and do a little bit of factoring. If I factor out an x from these guys, that gives me y minus 1 equals minus y, because we subtract this y, and then divide both sides by y minus 1. So I would end up having negative y divided by y minus 1. I'd, cancel out a factor of negative 1, which would turn this into y over 1 minus y. And then, you just pretend it's x all along. And so x over 1 minus x, answer C. Number 32. Which of the following does not have a period of pi? Oh, boy. Sorry for the slow sips here. I just don't want to dump coffee all over myself. I think a graphing calculator would help me here thinking about these periods, but I do want to try to minimize. So the period of sine is 2 pi, right? It climbs from 0 to 1 when you go from 0 to pi over 2, and then it goes back down to 0 as you go to pi, and then it goes down to negative 1 as you go to 3/2 pi, and then it comes back to 0 after 2 pi. Now, if we look at sine of 1/2 x, to have a full period, you got to go a total of 2 pi. But multiplying x by a half that means you're going to have to go to all the way to 4 pi to get a full period. So that doesn't have a period of pi, right? Yeah. I'm calling it there. That for sure doesn't have a period of pi, because if you're multiplying the input by a half, the input's going to have to travel twice as far in order to get a full period. When you get to 2 pi, you would only be halfway done. So done. 33. The absolute maximum of this guy on the closed interval occurs at, we got to just do the candidates test here, checking the candidates for maximum values. The candidates are the endpoints of our interval, right? They could be the endpoints, but we also have to check critical points. To find critical points, we first need to take the derivative. So we've got f prime equals 3x squared minus 6x. 12 becomes 0. Solve this for 0. If we solve it for 0, we'll factor out an x. And so we've got x times 3x minus 6 equals 0. You should also check if there's any points where the derivative doesn't exist. In this case, we don't have any of that to worry about. This gives us 2 possibilities, right? Either x equals 0 or x equals 2. So our candidates that we need to check are 0, negative 2, because that's an endpoint, 2, and 4. And we just have to answer the question, which of these x values has the biggest y value? If we plug in -2, let's just write this down. If we plug in -2, we get -8, and then that's going to be plus 12. Don't want to make a mistake here. And then plus another 12. So 24 minus 8, so 16. I'm guessing it's that one. That's pretty big, isn't it? I don't know. We'll see. What do we get if we plug in 0? We get 12, so it's not that. If you plug in 2, we get 8 minus 12, right? Minus 12, and then plus 12. So that's just 8, so it's not that one. And then if we plug in 4, we're going to get 4 times 4 is 16, 64, minus 3 times 16, which is 48, plus 12. 64 minus 48 is 16, and then plus 12 is 28. So pretty sure it's 4. I could have screwed that up, but I'm pretty confident in that one. So 28. I'll plug them in again if you want to double check, but I'm going with it. 34. Okay, area of the shaded I was afraid that it was going to be another volume problem. Let me take a sip of water. We were on problem 34, so we got 11 more multiple choices to go, and my timer tells me that, I don't know, you'll see a timer on screen, but I forgot to restart mine when I came back from my little break. All right, the area of the shaded region in the figure above is represented by which of the following integrals? So, what's going on here? Looks like we're probably going to need we got four integrals there. I mean, we got a couple options here, right? We could assess the validity of each of these responses, or we could just set up the integral ourselves and see which one it matches. Let me start with E, because I like the looks of E. I'm just going to check that one. E goes from A to B, so from here to here. And what it does is it integrates this guy, g of x, it integrates him, and subtracts f of x. And that would give us, let me just use a different color here, that would give us this area right down there. And then it adds from B to C. From B to C, it does f of x minus g of x. So then it takes the top function here and minus the bottom function. I think that one's right. The second part is definitely right. You can't just go from A to C in this case, because this area here is not going to work out if you do it like that. You know, I'm looking at like letter C. If you go just from A to C and do this guy minus this guy, that's not going to work out. Is it? No, I don't think that's going to work out. Yeah, I'm pretty confident in E. G of x minus f of x. G of x minus f of x. And then... well, then again, g of x is going to give us, right, a negative area down here. If you subtract f of x, you're actually going to be adding, because the f of x area is going to be negative. But that's not going to make the answer correct. It's still going to be a negative area. Okay, so maybe it's not E. What about D? If I go from A to C, and take f of x minus g of x, f of x is going to have some negative area here, but then it's going to be minus g of x, so it's actually going to be adding in all this positive area, that's exactly what I want, because it's going to give me this, but this will be negative, and everything here is going to work out. F of x minus g of x, because this area is positive, but it will be subtracting this negative area, which means it'll be adding it. Yeah, that's got to be it for sure. This one. Is that the, no, D, that's what I was talking about. F of x minus g of x. Yes, I'm confident in that. Subtracting the g of x is going to actually be adding those g of x areas that are underneath the x-axis, and that's what we want. So I'm going with D. Moving on, number 35. 4 times cosine of x plus pi over 3 equals what? Oh, this is like, it kind of looks like a trig identity type question, which makes me nervous. My heart's beating a little faster. Let me take a drink. I could just use my calculator, but obviously that makes this totally trivial. 4 cosine of x plus pi over 3 equals, oh, what an ugly mess. Isn't there, I don't know, there's some rule for like, if you add pi over 3 to cosine, if you add pi over 3 to the input of cosine, that's going to give you, I don't know, something to do with sine. Well, should I just draw it maybe? Draw a quick unit circle here. So if I got a unit circle, you got to remember the input is an angle. And so wherever cosine is at, some x coordinate, let me get this circle going. Wherever x is cosine of x, maybe I'm like right over here. If I add pi over 3 to that, which, maybe that's going to take me like right over here. Well, I don't know, maybe more like over here. It's tough to say. It's a tiny sketch. I mean, what's that going to give me? What is that going to give me? If I add pi over 3, but then it's also getting multiplied by 4? 4 cosine of x plus 2. I don't know. I don't think I'm going to get this one. I got to revisit those simple, trig. You're putting something inside of it. What's happening? I don't know. I'm skipping. 36. What's the average value of y for the part of the curve 3x minus x squared, which is in the first quadrant? So 3x minus x squared, we're in the first quadrant. So let's figure out where we enter and exit the first quadrant. To do that, I'll set x equal to 0 to see where we're going to hit the x-axis. That would give us y equals 0. No shocker there. And then I want to set y equal to 0 to see where the places that we would hit the x-axis. Obviously, one place is x equals 0, but where else? If we factor out an x out of this guy, we get 3 minus x equals 0. So the other solution we're looking for is x equals 3. That means our integral needs to go from 0 to 3. Average value means integrate the function and divide by the width of the interval. So I got to take this and divide by 3. That's not so bad. This is just 1/3 multiplied by 3 halves x squared minus 1/3 x cubed from 0 to 3. The 0, of course, is just going to be nothing, so I'm not worried about that. This is 1/3 times 9 times 3, 27 over 2. I'm just plugging in 3 right now. And then 27 divided by 3 is minus 9. Do we got fractions? Yeah, we got fractions, so this should be good. Okay, 1/3 of 27 over 2 is just 9 over 2, and then 1/3 of 9 is just 3. And so this is 9 halves minus 3, which is 3 halves. And there it is, letter C. All right, we're closing in on the end of the multiple choice here. On to 37. 37. If f of x equals e to the x sine x, then the number of zeros of f on the closed interval from 0 to 2 pi, e to the x is never 0. So this is just, how many times does sine of x hit 0? Sine of x is 0 at 0. It's 0 at 2 pi, and it's 0 at pi. So the answer is 3. 38. Oh man, this looks disgusting. What the heck? Okay, don't be intimidated. I say that a lot. Don't be intimidated by an ugly question. It might just be ugly, right? We got positive x. That's nice. We're integrating 1 over x times the integral of 1 over u du from 1 to x, and dx is getting applied to the outer integral here. I don't know if modern AP Calc has this type of thing in its curriculum, because this is, like a double integral. I haven't seen that in the current AP Calc curriculum, but that's fine. We're integrating 1 over u with respect to x. We're integrating 1 over u with respect to u first. So right now, it's just a constant, so no big deal. I've got 1 over x on the outside because we're going with respect to u first, so x is just a constant. I can have it pulled out like that. 1 over u becomes the natural log of u. The bounds are 1 to x. And then, of course, this second integral is with respect to x. And so this is the integral of 1 over x times the natural log of 1 is 0, so I don't got to worry about that. This just becomes 1 over x times the natural log of x dx. This is great. This is just a u sub problem. If I let u equal ln of x, its derivative is 1 over x dx, so we'll be good. Can I just totally skip the u sub here? I think I can. Yeah, I just see it in my head, right? U equals ln x, du is going to be 1 over x dx, so I'm just going to integrate u, so I'm going to have 1/2 u squared. I said that u was ln x, so it's 1/2 ln x squared plus c. And that is right there, 1/2 ln x squared plus c. All right, moving on. 39, try to power through the end of the multiple choice. And hey, after this, we only got 6 free response questions. I'm starting to feel really hungry. Okay, what's going on here? This is pretty easy, I think. We've got an integral from 1 to 10 that's given to us, and then an integral from 10 to 3. The insides of all these are the same. They're all f of x. And then we've got an integral from 1 to 3, and we want to figure out what that is. So all I need to do then, if I want the integral from 1 to 3, I just need to take the integral from 1 to 10. I'm going to use really sloppy notation here. I need the integral from 1 to 10, and I need to subtract the integral from 3 to 10. That will tell me what the integral from just 1 to 3 would be. And the integral from 3 to 10, I can find by just flipping these bounds. And flipping those bounds amounts to just bringing out a negative. So I could write this as negative 310 f of x dx. It's going to equal 7. Right? Because we're told that this thing equals 7, and you can flip the bounds if you take out a factor of -1. But then that, of course, means that the integral from 3 to 10 of f of x is equal to -7. And so I believe the answer is 4, this first integral, which is given to us, minus the integral from 3 to 10, which is -7. So 4 minus -7, so I think that's 11. Sorry, I don't think my explanation was great there. My throat is hurting. Just need some water in me, and here we go. Oh, is this related rates? Geez, haven't done that in a little while. The sides of the rectangle above increase in such a way that, our diagonal here, it's increasing at a rate of just 1. dx dt, this guy here, is 3 dy dt. That is its rate of increase. At the instant when x equals 4 and y equals 3, what is the value of dx dt? Well, that's not too difficult, is it? So if I want to find the value of dx dt when x is 4 and y is 3, then we just need to know what dy dt is. So to do that, let's probably just use Pythagorean theorem here. I know that x squared plus y squared equals z squared. You know, this is a rectangle, so this is a right triangle. And then I can get the derivatives involved by just taking the derivative of both sides. So that's going to be 2x dx dt. Remember, you know, in a related rates problem, it's often time that we're differentiating with respect to, because this is this is not a constant thing. It's changing, and so the derivative is with respect to time. And then plus 2y dy dt, and dz dt is just 1. So I mean, I can just write that right now. It's just 1. Okay, now what? Well, dx dt, I know, is 3 dy dt. So I can rewrite this as 2x times 3 dy dt. Nice. This is going to work just fine. Plus 2y dy dt equals 1. Yeah, we're trying to find dx dt. I'm going to find dy dt from this, which is fine, because then I can just plug it into this expression and find dx dt. So this will work. We're looking at x equals 4 and y equals 3. So let's plug that stuff in. Plugging in x equals 4, I've got 8, but times 3, so 24, dy dt, plus 2y becomes 6, so plus 6, dy dt equals 1. And so dy dt is going to have to equal 1 divided by 30, right? 1 divided by 30. And so that would mean that dx dt, which is 3 times dy dt, is going to be 1/10. And that's no good, because I don't see 1/10 as an answer. 24 plus 6, that's 30. Yeah, okay. Let's just check our work then. We set up the Pythagorean theorem, x squared. Oh, silly. Yep. Z squared, right? I forgot to square z. I'm sure you were shaking your finger at me when I wrote that. That was very silly. Let me take a sip of coffee. Man, I need a cough drop. My throat hurts. Okay, so at this step, we would have had 2z dz dt, but I know dz dt is 1, so that's it. X equals 4, y equals 3. We got to plug in a value for z now. If x equals 4 and y equals 3, classic Pythagorean triple, right? Z is going to have to be 5. Just plug it in and solve. Z is 5 using the Pythagorean theorem. So 2z over here becomes 10. That becomes 10 right there. And so instead of 1 over 30, it should be 10 over 30, which is 1/3. Is this going to work? Yeah. And then it's 3 times that. So just 1. Just 1. Letter B. Nice. All right. Just check my technology. Everything's working. I got batteries. 41. I need water. All right. Man, this is exhausting. I'm glad I don't have to do this, except by choice. If the limit of f of x as x approaches 3 equals 7, which of the following must be true? You don't have to be continuous. That's definitely not necessary. The limit just tells us what's happening as we approach x equals 3. Doesn't tell us what happens at x equals 3. None of this has to be true. F doesn't need to be differentiable at x equals 3, since it doesn't even need to be continuous. And obviously, f of 3 doesn't need to equal 7. It could just jump at x equals 3. So this is like the easiest question yet. The answer is none. Sure hope I didn't get that wrong. 42. The graph of which of the following equations has y equals 1 as an asymptote? Y equals 1 is like this, right? It's horizontal. So it would be a horizontal asymptote, which means we're looking for functions that have a limit of 1 as x approaches infinity or negative infinity. That's the type of thing we're looking for. I recognize this guy, right? As x approaches infinity, that's getting really close to 1, and I can't pick multiple answers, so I'm done there. As x approaches infinity, this gets super, super close to 1. same thing happens as x approaches negative infinity. So I just recognize that guy. Easy. Next one, 43. The volume of the solid obtained by revolving the region enclosed by the ellipse. Hopefully we have better luck with this volume problem. About the x-axis is what? The volume of the solid obtained by revolving the region enclosed by the ellipse x squared plus 9y squared equals 9. About the x-axis is what? Okay. All right, trying to remember the equation of an ellipse, right? We want the variables to be divided by squares. And I think we want a constant of 1 on the other side for an equation of an ellipse. So if I divide both sides by 9, my equation looks like this. X squared over 9 plus y squared over 1 equals 1. And this tells me that I've got an ellipse centered at the origin with a major, an x-axis of 3 is its like major radius. So if I start to graph this, it's going to look like there's 1, 2, 3, 1, 2, 3, y equals 1, y equals negative 1, and my ellipse looks, really, really roughly like that. That's pretty bad, but it's tough to draw on an iPad where there's no friction. And this is getting revolved, the volume of the solid obtained by revolving this region about the x-axis. So, this is just this beautiful, like, football type shape. Okay, so, yeah, we got circular cross sections, right? If you take any slice of this thing that's been revolved around the x-axis, take a vertical slice, it's going to be a circle. The radius of the circle is just the value of the upper half of the function. And so I've got to integrate from -3 to +3 pi r squared. Pi I take out. The r squared, again, it's like the height of the function. That is the radius, because the circular cross sections are going to look something like that. Yeah, there we go. That's a nice picture. And so I just want to solve this guy for y. Yeah, that's going to give me the radius. That's going to be good. Wonderful. Okay, so solving this for y, that's going to tell me that y has to equal the square root of 1 minus a 9th times x squared. Oh, I don't think I want to integrate that very much, do I? 1 minus a 9th x squared. 1 minus a 9th x squared. Yeah, 1 minus a 9th x squared. I didn't do that wrong, did I? Nope, that looks good. Okay, so this is pi times the integral of the square root of 1 minus a 9th x squared dx. Okay, so that's it's symmetric, so we could just go from 0 to 3 and double it if we wanted to. That doesn't really change anything as far as the integral is concerned. And when I'm out, I'm looking for that vintage fling. But all complexions that I adore, so hard to find, these seem impossible to... Oh my God, I can't believe this. I'm going to have to fast forward that in editing. I forgot to square it. It's got to be squared because it's pi r squared. That's the area of the circular cross sections. Whoops. So this is equal to, make sure that all my devices are still working, 2 pi times the integral from 0 to 3, 1 minus a 9th x squared dx. This is just power rule. So 2 pi multiplied by x minus 1/27th x cubed going from 0 to 3. I need some water after all that. All right. I'm going into the next problem with the work here, but bear with me. 2 pi multiplied by, plugging in the bounds now, 3 minus 27 over 27, so 3 minus 1. And then minus, plug in 0, it's just 0. So I got 4 pi. 4 pi, oh yeah, it's letter B, finally. Moving on. I'm just going to have to like circle all this work and shrink it. You know, I could do that or delete it, but I'm just going to shrink it and leave it there. Big mess. Okay, clearly I need to practice the volume problems. Let f and g be odd functions. Odd functions mean they've got like, 180-degree rotational symmetry. So f of negative x equals negative f of x. Let f and g be odd functions. If p, r, and s are non-zero functions defined as follows, which must be odd? I don't know this off the top of my head. This seems like a strange problem. P of x, it's a non-zero function. It's equal to a composition of odd functions. Is a composition of odd functions odd? Yes, a composition of odd functions is odd. So 1, I believe, is odd. I think that's true in general. I'm just going through like a specific example in my head. Like if you plug x to the 5th into x cubed, it's x to the 15th. That's odd. So I'm guessing that's always true. Composition of odds is odd. Yeah. Letter 2, or number 2, r of x equals f of x plus g of x. Well, I don't think so. Because, if I add like x, if I add x cubed, well, x cubed plus 1, that doesn't count as an odd function, right? F of x equals x cubed plus 1. It has exactly the shape of an odd function, but because it's been shifted up 1, it's not technically odd. Because if I plug in like negative 1, if this function were odd, that should be the same as negative f of 1. But I don't think that would hold with this guy, because f of negative 1 would be 0, and negative f of 1 would be negative 2. Yeah, so I don't think adding odd functions is going to give you an odd function. Not necessarily, anyways. Option 3, product of odd functions. No, for sure not, right? Because x cubed is odd, multiply them, it's x to the 6th, which is even. So I'm going 1 only. I think I feel pretty good about that, especially because there's no option that says they're all wrong, so for sure it's got to be A. 45, it's the last one, last multiple choice. Let's go. First glass of water done. I got a square root of 2 glass here. I know I'm way over an hour and a half, but it's because I'm explaining every problem, so it takes a lot longer. The volume of a cylindrical tin can with a top and bottom is to be 16 pi cubic inches. A minimum amount of tin is to be used to construct the can. What must be the height in inches of the can? Okay, fun problem. So we want a minimum amount of tin used. So we're trying to minimize surface area. So we want a expression for surface area. And surface area, volume, bottom. Surface area is going to be 2 pi r squared to give us the area of the top and the bottom, plus pi r squared times the height, h. That's the surface area. No, sorry, that's volume there. We've got to capture like the area of the main body of the cylinder, which is like a rectangle. It's if you unfold it, it's a rectangle, and its area is the circumference of the base times the height. So it's got to be 2 pi r. That's hideous. 2 pi r try to undo this. 2 pi r, that's the circumference of the base, times the height. So that's the surface area. And I'm trying to minimize this amount of tin that's used to construct the can. I know that the volume, which is what I wrote a minute ago, pi r squared h, I know the volume has to be 16 pi. Okay, so that means pi r squared h equals 16 pi. So if I divide both sides by pi, that would tell me that r squared h equals 16. So I guess I could solve for h, and that might work. Yeah, h equals 16 over r squared. And now my function for surface area becomes 2 pi r squared plus the r and the r squared will partly cancel out. It's going to be 2 pi r to the negative 1. Yeah, so now I got an expression for surface area.
So I dream on to someday find that vintage love. I kept on looking, but everyone's such a bore. And out of a sudden, you came through the door.
I guess I'd have to go with C, you know, if I'm doing this test, because I have a cube root of 4, so C? I don't know. So that's the end of the multiple choice section. I'm sure that took me way longer than 90 minutes since I was explaining the whole thing. But we'll move on to section 2, the free response questions. I'm going to take a little break, though, to just recharge these devices, get some more water, and I'll see you for the free response. All right, I recharged my devices. I emptied out my SD card. I went to bed. It's the next day. My throat really, really hurts. I don't know why, if it's just all the talking I did yesterday. Usually I talk plenty, so maybe I'm sick. But forgive me if I sound a little less enthused for the second half of this video. Just try to not, hurt myself too much. But I am in immense suffering as I am here before you to do the rest of this exam. We've got the free response questions left. I haven't looked at them, so going in fresh here. Hopefully they go all right. I already graded my multiple choice section. I know I got 4 wrong, so try to do the problems I got wrong. Give me a nice solution down in the comments. That'd be great for everyone. Made a couple silly mistakes, but yeah, so it was all right overall. Let's head on to the free response section. Another 90 minutes. I'm going to start my stopwatch with my phone over here. We got 6 problems. Let's see how it goes. Question 1. Let f be the function given by this square root, which has got a difference of squares inside of it. Letter A, find the domain of f. If I want to find the domain of f, the only problem, of course, is the square root. So we just need this thing in here to be non-negative. If x is 0, then this thing will be 0, so that will be fine. X can be 0. Besides that, we just need the thing to be positive, which means x to the 4th is going to have to be greater than 16x squared. Greater than 16x squared. Now, if x is positive or negative, obviously, since these are even powers, the numbers are all going to be the same. Let's just go ahead and divide both sides by x squared. That's going to give me that x squared is greater than 16. And so then that means x is going to have to be, more than 4 away from 0. Its absolute value has to be greater than 4. Its absolute value has to be greater than 4. Oh, and what if it equals 4? If it equals 4, then x to the 4th would be 16 squared, which is 196, and 16x squared would also be 196. So that would also be a possibility if x if x is equal to, what did I say, 4? Yeah, so the absolute value of x could be greater than or equal to 4. If it's equal to 4 or negative 4, then this stuff in here is going to be 0, which is fine. If x is 0, this will be 0, which is fine. And if the absolute value of x is in fact greater than 4, then x to the 4th will be greater than this guy, and so the input will be positive. So x could be 0, 4, negative 4, or anything that's more than 4 away from 0. So final answer, the domain here is going to be all real numbers x, such that x is equal to 0, or the absolute value of x is at least 4. That would be my domain. And now I'm just wondering, is there any work that I should show here to get like full credit for the way they would score the free response question? I think this is probably fine. I'm going to leave it there. I'm not going to worry too much about the expected work. I'm going to do the work I need to do and carry on. Question B. So this is still the first free response question. We've got to describe the symmetry, if any, of the graph of f. Describe the symmetry. Well, if I used a graphing calculator, that would make this very easy. Well, let's write it in terms of y. So y equals the square root of, what is it, 4, 4x to the 4th? It's just x to the 4th. X to the 4th minus 16x squared. And then if I go ahead and square both sides of this, I get that y squared equals x to the 4th minus 16x squared. So that doesn't, it's not a circle. It's just, it's just one of these nasty square root functions. Well, what symmetry could it have? It's asking about the graph, right? And the graph is only going to exist above the x-axis because it's a square root, and so you can't get negatives. I could plug in negative values of x, though. Yeah. So we gotta, we can't miss that. It's what we call an even function, right? If you reflect it across the y-axis, it's going to look the same, because if x is negative, then f of x is still the same thing, because x is just getting raised to even powers, so the negatives kind of just vanish. So if x is negative, f of x would be the same as f of negative x, and negative x would be a positive number, if we're talking about x being negative. You could also just delete that, right? And just say, hey, f of x equals f of negative x, as long as x is in the domain of our function. It's got to look something like that. And so the symmetry, I would describe it as even. It's an even function. Symmetry, I just say even. It's even. It's, symmetric. Symmetric if you reflect it about or across the y-axis, rather. Symmetric when you reflect across y. I would be a little more careful with my writing here, if I was actually doing the exam, but just trying to make my thought process clear. Symmetric when you reflect it across the y-axis. Find f prime of x. That's easy. That's the easiest one so far. It's just chain rule. X to the 4th minus 16x squared. That's what the function is, right? X to the 4th minus 16x squared. Good idea to rewrite this stuff with powers. I say that a lot, so I'm just going to write this the same way, but with a power of a half. And so then f prime is going to be bring the power of a half down. Don't touch the inside function. Just leave it be. Reduce the power by 1, and then multiply by the derivative of the inside function, which is 4x cubed minus 32x. And I'm going to leave it like that. I mean, I guess we could distribute the 1/2 if we wanted to. So turn this into 2x cubed minus 16x, and then times x to the fourth minus 16x squared to the negative half. Is there factoring potentially that we might want to do here to simplify this? Well, this is a difference of squares, but it's all wrapped up in a square root, so I don't think that would really get us anywhere. No, I'm pretty content with that. 16x squared, 16x. Yeah, I don't think we're going to be able to cancel anything out if we do factoring here. All right, part D. Geez. Find the slope of the line normal to the graph of f at x equals 5. I'm pretty sure this is not in the AP curriculum anymore. I certainly didn't see it. So I'm not sure how they want you to do this. I would use a cross product, with vectors and stuff. Find this, well, that's probably not necessary, right? I mean, we could just, perpendicular lines are pretty easy. Normal, by the way, if you don't know, normal means perpendicular or orthogonal. We want to find the slope of the line. We just need a slope. So yeah, this is really easy. You just have to know that normal means perpendicular. Find the slope of the line normal to the graph of f at x equals 5. So all I'm going to do is plug x equals 5 into the derivative. That's going to give me the slope of the tangent at that point. And the normal is going to be perpendicular to the tangent. So I just need to take the negative reciprocal of the slope that we get here. F prime of 5, let's plug it in. 2 times 5 cubed, that's going to be 250. And then 16 times 5 is 80. And then 5 to the power of 4 is 25 squared. And I think that's, is that 625? 625, I believe, minus 16 times 25. I can do that, right? 16 times 25 is going to be 250 plus 100, 350 plus another 50, 400, I believe. What did I just do? 16 times 25. I'm pretty confident in 400, although this isn't multiple choice, so I'm not going to know if I screw it up. Let me just do that one more time. 16 times 25. Yeah, that's super easy. Yeah. To the negative half. Okay. 250 minus 80 is going to be 170, and that's getting multiplied by let me turn this into a fraction now. 170 divided by the square root of 625 minus 400 is 225, 225. The square root of 225 is 15, so this is 170 divided by 15. Let's cancel out factors of 5, so this is going to be divide by 3, and how many times does 5 go into 70? 14 times, so this is 34 over 3. Yep. That's fully reduced. That is fully reduced, right? 17 to, yeah. Yep. And so the slope of the line normal is going to be the negative reciprocal of this. So our answer is negative 3/34. All right, I bet you that's the last part of this question. Yes, it is. Fantastic. A through D, that's not so bad. We are 10 minutes in. Okay, keep going. A particle moves along the x-axis so that its velocity at any non-negative time t is given by this function. Find the acceleration. Acceleration is just the derivative of velocity, so we'll take the derivative of velocity with respect to time. 1 becomes 0, minus sign becomes minus cosine. Don't touch the inside function, but you do have to then multiply by its derivative, which is just 2 pi. And so the velocity is negative 2 pi, cosine of 2 pi t. Man, I hope I'm not sick. That would really be a bummer. Okay. B. Find all values of t for which the particle is at rest. All values of t between 0 and 2. Okay, wonderful. So for the particle to be at rest, we need it's tempting to just use the function we just found, but that's not the one we want. We want to use the original velocity function. When that's 0, the function, the particle is at rest when the velocity is 0. So the velocity is 1 minus sine of 2 pi t, right? 2 pi t? Yeah. 2 pi t. 2 pi t. So for the particle to be at rest, sine of 2 pi t needs to be equal to 1, so that we'd have 1 minus 1. Sine of 2 pi t needs to equal 1. And sine equals 1 at the pi over 2. Pi over 2 is where sine is 1. So I'm just going to set the input equal to pi over 2. It's got to be pi over 2 in order for sine to be 1. And that's going to give us that t is equal to 1. That's got to be it. There are other values of t, where the particle would be at rest since sine is periodic, but we're focused on t being between 0 and 2. And so I believe, oh, wait a minute. No, that doesn't make any sense at all. It's not 1. Whoops. It's 1/4. 1/4, right? You plug in a fourth, and you're going to get pi over 2. And there's no other value for t between 0 and 2 where that's what you would get. Is there? Yeah, there is. Because going from t equals 0 to t equals 2 is going to be 2 full periods of the sine function, because 0 to 1 is going to get us through 2 pi. And then 1 to 2 is going to get us through another 2 pi. So I believe if we just add 1 to this, that would jump us into the next cycle of sine. So I believe t equals 5/4 would also work. Just plug it in to check. If you plug t equals 5/4 into this thing, you're going to get t equals 5/2 pi, which is 2 pi plus another half. So that would be 1 is what the value of sine would be. So those are the two options. T equals 1/4, t equals 5/4. I'm trying to go, no calculator at all for this entire exam. Obviously, you could really do this pretty easily with a calculator. All right, we're 15 minutes in. We're on to part C. Find the position at any time t if x of 0 equals 0. So this is integration, right? To find the position function, you need to integrate the velocity function, and you'd end up with an arbitrary constant unless you have an initial condition, which we do. So we'll be able to solve for the arbitrary constant. So the position function, we're going between 0 and 2, right? That's the deal for this whole question. No, we're going from 0 to t so that I can get a position at a time t. And the velocity function is 1 minus sine of 2 pi t. So I'm going to do 1 minus sine of 2 pi z, just to use a dummy variable, because I don't want to integrate with respect to one of the bounds. That's not a thing we can do. So that's what I'll do. The position is going to be the integral from 0 to time t of the velocity function, and I'm just using the z variable here. And this is going to equal, let's see, 1 becomes z, and sine is going to become plus cosine, because cosine gives us the negative. So plus cosine of 2 pi z, but then we would also have to multiply by that derivative of z, which is, oh no, whoops, it's so easy to do that. I started differentiating for a second. We need to divide by the derivative of the inside function because we're doing differentiation, right? This is a situation where you could use u sub, but it's really not necessary since the inside here is a linear function. It's pretty easy to just figure it out as you go. I need this to be cosine of 2 pi z, all divided by 2 pi. That way, the cosine is going to give me minus sine when I differentiate. And then the 2 pi will cancel out with that 2 pi that comes from the chain rule. And this is going from 0 to t plus an arbitrary constant. So this is equal to t plus cosine of 2 pi times t divided by 2 pi, and then let's subtract, plugging in a bound of 0. Plugging in 0 makes that 0, and cosine of 0 is 1, so this just becomes 1 over 2 pi plus c. That's kind of ugly, isn't it? 1 over 2 pi. If you plug in 0, yeah, cosine of 0 for sure is 1. So, all right, I guess it's minus 1 over 2 pi, which, we could combine this fraction and this one if we want, and I do want, so let's go ahead and do that. This becomes cosine of 2 pi t minus 1, all over 2 pi, and then plus c. So that is our position function. Now we just need to plug in 0 and use that initial condition in order to solve for the arbitrary constant. So I know that x of 0 is equal to 0, and using our function, it's equal to, I'm just plugging in 0 for t, it's equal to 0 plus cosine of 0 minus 1 over 2 pi plus c. Cosine of 0 is 1, minus 1 is 0, so all of this is 0, including c. C's got to be 0. All right, so that's our final position function right there. T plus cosine of 2 pi t minus 1 over 2 pi. Not super beautiful, but I don't feel unsure about any of that, so I'm going with it. All right, 3. Getting to the halfway point of the free response section, almost 20 minutes in, so we're making good time. Let R be the region in the first quadrant enclosed by the hyperbola x squared minus y squared equals 9, the x-axis, and the line x equals 5. Oh, hyperbolas. I don't have much practice graphing hyperbolas. And we want to find the volume of the solid generated by revolving R about the x-axis. Find the volume of the solid generated by revolving R about the x-axis. Okay, well, let's get started on this graph here. X equals 5 is going to look something like that. Just try to make this a nice dotted line. That is our x equals 5. And then we've got our hyperbola, x squared minus y squared equals 9. Now, that's going to look something like that, right? And we're in the first quadrant. I believe this is what that's going to look like. And we got the line x equals 5. Then we're revolving it around the x-axis. So we just have a bunch of circular cross sections. Yeah, I think this should be pretty easy. Let me just plug in some points here, though, to make sure that my graph seems plausible. Yeah, it does, right? I mean, if I plug in something for x, then since y is squared, I'd have 2 possibilities for y, something up here or something down there. I'm confident in this graph. It's good. Moving on. The volume of the solid generated by revolving this region about the x-axis, well, the region is actually this one, because we're in the first quadrant, but then we're revolving it about the x-axis. So our cross-sections, our circular cross-sections, are going to look something like this. Just try to give you a rough outline of one. Something like that. That's what our circular cross-section's looking like. The radius of the circular cross-section is the heights, the upper half of the function, if we were to turn this into a function, which we'll have to do. So setting up our integral, we've got to go from x equals, we have to figure that out, right? Where is it going to hit the x-axis? Got to figure out where to start. Well, where it hits the x-axis, y is 0. So this is x squared equals 9. So it's got to hit the x-axis when x is 3. Again, we're focused on the first quadrant here, so that's why I'm going with the positive solution. So we're going from x equals 3 to x equals 5. I'll mark that right there. That is, well, actually, I need to redraw it if I want to keep my scale, because I said that's 1, 2, 3, 4, 5. So let's redraw it. I'm just going to move move this character over, see if I can select him without selecting the x-axis also. But I got the dotted lines here. That's going to be tough to move. Sorry, let me get rid of the dotted lines because that's going to be awkward. Okay, now I'll move my hyperbola. It's going to go all the way up to x equals 3. So 1, 2, 3, sure, something like that. And if I just want to redraw a cross section, it's looking something like that. A little bit of a mess, but hopefully you get the picture. All right, let's set up the integral. It's pi r squared from 3 to 5. The radius is just this relationship, but solved for y. And if we solve it for y, we're going to get the square root of x squared minus 9. And this time, I'm not going to forget to square it. We got to square that because it's pi r squared dx. Yes, I feel good about that. Yep, 3 to 5, everything looks good. And so we are integrating from 3 to 5, just x squared minus 9, very easy integral. This is going to be pi multiplied by a third x cubed minus 9x from 3 to 5. Now we just got to plug in our bounds and be done with it. Pi multiplied by 125 divided by 3 minus 45, and then minus 27 thirds. I'm plugging in 3 now, and plus 27. This makes you want to bust out your calculator at this part, but I'm not going to do it. Pi multiplied by, let's combine the thirds, and let's combine the whole numbers here and go from there. 125 minus 27 is just 98 thirds. And 98 is not divisible by 3, so that's too bad. Minus 45 plus 27 is minus 18, so subtract 18. And then I'll just bring these two fractions together. 18 consists of... I don't want to screw this up. 18 consists of 54 thirds. So in total, I've got pi times 98 minus 54, which is going to be 44. So 44 thirds, because 18 is 54 over 3. 54 over 3. So yeah, that looks good. Okay, it's slightly awkward answer, but I've definitely seen uglier ones. So 44 pi over 3. Final answer. Moving on. Part B. Set up but do not integrate an integral expression in terms of a single variable for the volume of the solid generated when r is revolved about the line x equals -1. An integral expression in terms. So this, now they're not restricting us to one quadrant, which is too bad. So what's the solid generated when r is revolved about x equals -1? Let me just grab the graph and bring it down here, and we can think about this. How many parts left are there to this one? This is the last one. Okay. Let's do it. We can handle this. We're revolving about the line x equals -1. So that's maybe right here. This is, let me just draw like a nice dotted line, technologically assisted. Looks something like that. That's x equals -1. And the half of the parabola over here, it starts at x equals -3. Sorry, I said parabola. I meant hyperbola. It's looking something like this, something like that. And so we're revolving this whole thing about the line. Oh, ooh, look at this, right? It's still saying big R, the region big R from before. We're still talking about the same region. Yeah, I was about to say, this seems a little ambiguous. So we're still talking about this region between x equals 3 and x equals 4. No, x equals 5. Why did I write x equals 4 here? I don't know where that came from, but I have 5 there, which is right, so just ignore it. I don't know why that says x equals 4, but going between x equals 3 and x equals 5, this region is getting revolved about the line x equals -1. Oh, okay, so that's like a sort of donut-y type shape. About the line x equals -1. It's a donut type shape with a flat-ish outside. What the heck is this gonna look like? Okay, I thought about it. I think using the washer method with respect to y should be fine. I was trying to use that method in a multiple choice question, and it just wasn't going to work because the way I wanted to do it wasn't represented as a multiple choice option. But this is free response, so we should be fine. If you revolve this region about x equals -1, then you're going to get like a big outer circle that comes from the x equals -5, just rotating around x equals -1. And that outer circle is going to have a radius of however far away x equals 5 is from this line, and that distance is 6. And then, you're going to have like, well, really what's a cylinder is what you're going to have. It's this big cylinder, but then a bunch of it is being like cut out by this bottom function, the hyperbola, that is also rotating about x equals -1. And if you take one of those circular cross sections from it spinning around x equals -1, the radius of one of those guys is it's a little more awkward, but it's going to be 1. It's going to be 1 to get from, here to here. And then it's going to be the x coordinate of, wherever you are. So it's 1 plus x. You got this distance x, and then you also have to add 1. And that's going to be the radius of the circle that's created by revolving this thing about x equals -1. So I need to calculate the volume that results from the revolution about x equals... Sorry, let me rephrase that. I need the volume that results from the revolution of x equals 5, and I need to subtract the volume that results from the revolution of the hyperbola. And we're going to have to go with respect to y, because I'm imagining, taking out these washer-type cross-sections along y. So if I set this up, first thing we might think is, what are the bounds on y? And the x equals 5 and the hyperbola are symmetric about the x-axis. So I'm only going to focus on the part of this that is above the x-axis. Yeah, that's what I'm going to do. And so I'm going to multiply this thing by 2 and just focus on the part above the x-axis, which means my y is going to go from 0 to whatever the y is here when the curves intersect. And the curves are x squared minus y squared equals 9 and x equals 5. So that would be 25 minus y squared equals 9. So y squared equals 16. So they intersect at, it's y equals 4 right there. So I got to go from y equals 0 to y equals 4. I'm going to need to factor out a pi, because now what's going in here is pi r squareds. So I'll factor out a pi. And then I need the r squared that comes from the outer function, subtract the r squared that comes from the inner function. So the r squared from the outer function is 6 squared, which is 36. Subtract the r squared from the inner function, which is 1 plus x squared. But I'm going with respect to y, so I need to write x in terms of y. To do that, I'm going to need to take a square root which restricts myself to the positive values, but that's fine because, I already said I was going to do that. So it was x squared minus y squared equals 9. I'm solving for x in terms of y, so x equals the square root of 9 plus y squared. Yes, that looks good. So the integral is 36 minus, this guy is a radius and it's getting squared. So it's 36 minus 9 minus y squared. The square root disappears because I squared it. And then this is going to be, just rewriting it down here, 2 pi multiplied by the integral from 0 to 4 of 27, because 36 minus 9, minus y squared dy. That's my volume. I'm going with that. We don't have to actually integrate. We just have to set it up. So question done. We can move on. I hope I got that one right. It's similar to a multiple choice question that I got wrong. So hopefully this doesn't, shed a very bad light on my skills with these volume problems. Here we go. Question 4. We're just over 30 minutes in. Let's see.
Okay, long story short, the last recording cut out because I started having a bunch of tech problems. It just stopped my audio recording, and I gave this question here, question 4. I went through it twice, but it kept cutting out my recording. And also, it turned out I was sick, and so now it's several days later. I'm still sick, but my throat doesn't hurt so much anymore. I'm just kind of stuffy and lightheaded and all that. Okay, so we're going to finish the exam. I got question 4 now to go through. It's not fresh. I've gone through this problem twice, but it's been a couple days. So let's get into it. We're moving on. Gonna finish this darn exam. What an affair. Okay, question 4. Let f be the function defined by f of x equals 2x e to the minus x for all real numbers x. Part A is we want an equation of the horizontal asymptote for the graph. A horizontal asymptote happens when x approaches infinity and a function gets closer and closer to some value, or when x approaches negative infinity, a function is getting closer and closer to some value. So let's check the limit of the function as x goes to infinity. What we'll notice here, as x goes to infinity, e to the minus x is going to be 1 divided by really, really big numbers, right? Because a negative power means this is 1 over e to the x. So this is 1 over e to really big numbers, and the numerator would just be 2x. E to the minus x is going to totally be bigger than just 2 times x. So this is going to be going to 0. If you plug in some really big number for x, you'll see that you're going to get something real close to 0. So that's going to be one of our horizontal asymptotes, y equals 0. As x goes to infinity, the function's going to go to 0. We should also check what's going to happen as x goes to negative infinity, if the function happens to be approaching some finite value in that direction as well. We could have another horizontal asymptote. In this case, though, we won't, because e to the negative x, as x goes to negative infinity, that's just going to be e to really big positive numbers. And then that's going to be getting multiplied by 2x, which is going to be just really big negative numbers. So as a whole, this is just going to be a really big negative number. It's going to be going to negative infinity. That's what this limit is. And since that's not a finite value, that means this is not a horizontal asymptote. The function's not getting closer and closer to some number as x goes to negative infinity. So that's our answer, y equals 0. All right, part B. Find the x-coordinate of each critical point of f. Critical points where the derivative is 0 or undefined. For each such x, each critical point, determine whether the function's value at that point is a relative max, relative min, or neither. Okay, so our function f of x, as you may recall from part A, is 2x e to the minus x. So to take the derivative of this, we just got to bust out our friend the product rule. I'm going to call this guy here f and this guy g. I know that, we already called the function f, but I hope you'll play along as we just conveniently use this notation for the product rule. So product rule is going to be f prime g. So f prime, that's 2 times g, so 2e to the minus x. F prime g plus g prime, which is going to be minus e to the minus x. That's because the derivative of e to the minus x is just e to the minus x, but by the chain rule, you got to multiply by the derivative of the exponent. So that's g prime, and we got to hit that with a factor of f. So g prime f is that. Okay, so that's the derivative. Now, where is this thing undefined? Well, the only potential problems would be the e to the minus x's, because those are things in the denominator, and we can't have those equal 0. But there's no power we can raise e to get 0. So in fact, the derivative is defined everywhere. So the only possible critical points are going to be where this thing is equal to 0. Now, let me switch away from this green marker. I don't really like that. We need the derivative to equal 0. Those will be our critical points. So let's try this out. 2e to the minus x plus, well, actually just minus 2x e to the minus x. That's this second half. This equals 0. What's that going to give us? Well, we'll add 2x e to the minus x to both sides and divide everything by 2. So e to the minus x is going to be equal to x e to the minus x. And then divide everything by e to the minus x, which of course we know is non-zero. And that leaves us with x equals 1. And if we plug that back in here, that checks out. If you plug in x equals 1, the derivative is 0. That's our one critical point. So then we have to determine, is this a relative maximum, a relative minimum, or neither? Now, a quick and easy way to check that is with the second derivative test. We just have to look at the second derivative. And if the second derivative is positive at x equals 1, that means the function is concave up. And so this would have to be a minimum. And similarly, if the second derivative is negative, it's concave down. And so this would have to be a maximum. So let's just take the second derivative. To take the second derivative, we'll start by differentiating that term, which is just going to be minus 2 e to the minus x. And then what you should notice is this other term we have to differentiate is actually just the original function, 2x e to the minus x, except with a negative factor. So to differentiate it, I can actually just pull out a negative factor and then copy and paste the original derivative, because it is just the original function. So just like that. Again, this guy here is the original function, just with a negative factor. So I pull out the negative factor, and I'm left with, what was I talking about? The derivative. This guy's the original function. So we can just take the entire derivative of the original function, and that's what goes here. I just confused myself with that explanation, but hopefully you follow what I'm saying. And so now I could try to simplify this if I wanted to. I don't really feel like it. I'm just going to plug in x equals 1, and we'll see if it's positive or negative. So f double prime of 1 is going to be equal to negative 2e to the minus 1 minus 2e to the minus 1 minus, that's going to be a plus. So plus e to the minus 1 times 2. Okay, minus 2e to the minus 1 minus 2e to the minus 1 plus 2e to the minus 1. These guys are going to cancel out, right? That's a minus 2e to the minus 1 and a plus 2e to the minus 1. So we're just left with minus 2e to the minus 1. That, of course, is negative, and so x equals 1 has to be a relative maximum, because a negative second derivative means this is concave down. So this guy's chilling at the top of some sort of peak. It is a relative maximum. Make sure I spell that right. All right, next part. For what values of x is the graph of f concave down? It's going to be concave down when the second derivative is negative. So let's just copy and paste our second derivative. We just want to figure out when this guy is negative. There's our second derivative. Okay, to see when it's negative, we'll want to simplify it a little bit, I suppose. So let's start there. Just simplifying, this is negative 2e to the negative x minus 2e to the negative x plus 2x e to the negative x. Okay, and so in total, this is minus 4e to the negative x plus 2x e to the negative x. And then we can factor, let's factor a 2e to the minus x out of this. So 2e to the minus x. And then what's going to be left in this term is just x. And what's going to be left in this term is minus 2. Okay, so right now we're trying to find where is this guy negative, because that's where our function is concave down. So where is this thing less than 0? Well, this term here, 2e to the minus x, will always be positive because e to a power is always positive. So the thing's only going to be negative when this guy is negative, x minus 2. X minus 2 would have to be negative, which would mean x is less than 2. That's where the function is concave down because that's where the second derivative is negative. Okay, so far so good. Part D is we want to use the results we've found so far to sketch our function in the xy plane. This is one of the real cool things about calculus. You can take these derivatives and find maxes and mins and get a decent sketch of a function, even if it's kind of, not a function you might immediately recognize. So let's check the information we've got. When x is less than 2, all the way over here, our function's got to be concave down, so it's going to be looking, something like that. But before we sketch that, let's check our extreme value. X equals 1 is a relative maximum, so let's plug 1 into the function to see what that maximum has to be. The function is 2x e to the minus x, so this is 2e to the minus 1, or 2 over e, which is, a little bit less than 1. So if I plot that on the graph, it's going to look something like that. Plug in 1, that's what it looks like. That's the maximum. Now, we found that when x is less than 2, this guy has to be concave down. Let's go ahead and plug in 2, just to see what happens there. Then we're going to have 4, because it's 2x e to the minus x, 4e to the minus 2, right? So that's 4 over e squared. That's also less than 1. And it's going to have to look, something like that. So this guy is looking like, that was at x equals 2 is what that's supposed to be at. So this guy's looking something like this, because this is a maximum. It's got to be concave down, which is why it looks like that. What about where it hits the x-axis? Where does it hit the x-axis? I guess that would be at x equals 0, right? So let's correct that. At x equals 0, this guy hits the x-axis, so it should look something like that. We already discussed how it's, whoops, man, I hate how that happens sometimes. Like it just goes flying. Why does it do that? We already discussed that as x goes to negative infinity, the function goes to negative infinity, so it should look something like that. And we discussed that as x goes to positive infinity, the function goes to 0. That was a horizontal asymptote. So this is my sketch of the function. 2x e to the minus x looks something like that based on everything we've discussed. And then one other thing, no part of the problem asked us where it equals 0, but that helps us with our picture. Obviously, if x equals 0, then the function equals 0 based on its definition. All right, that is all of free response question 4. We only have 2 to go. Moving on to part 5. I'm just going to wipe my nose real quick. All right, here we go. Question 5. Let R be the region in the first quadrant under the graph of y equals x over x squared plus 2, x is going between 0 and the square root of 6. And we just want to find the area. Yay, no volume. Find the area of the region. So should be a simple integral from x equals 0 to x equals root 6, unless anything weird happens in that interval. But I don't see any reason why something strange would happen. The function's not going to cross the x-axis on that interval. It's not going from positive to negative. We could do a quick sketch just to get some idea of what this thing's going to look like. I notice since the denominator is of a higher degree than the numerator, it should be approaching 0 as x gets bigger. And if I want to just plug in a couple points, if I plug in x equals 1, I'm going to get that y equals 1/3. If I plug in x equals 0, I'm going to get y equals 0, of course. Did I do that right? Yes, I did, of course. Y equals 0. If I plug in x equals, let's say, a half, I'm going to get y equals a half divided by a fourth plus 2. A fourth plus 2, which is, 9/4, right? A fourth plus 2, 9/4. Yeah, 9/4. And that's equal to, 4/18? Is that right? 4/18? Yeah, you multiply by 4/9. Yeah, 4/18. Okay, that's fine. So if I just plot a couple of these points here, if x equals 1, y is 1/3, maybe I put that there. If x is a half, then y is 4/18, which is less than 1/3. So, if this is y equals 1, then maybe, let's see, maybe this other point is like right here. Okay, so something like that. That's kind of weird. X equals 1, 1/3. Yeah, what if I plug in x equals 2? If I plug in x equals 2, then y is going to equal, wait, is it 1/3 again? 2/6. Yeah, y is 1/3 again. Okay, so if x equals 2, y is 1/3 again. So maybe we're going up here, but then we start coming back down and approaching 0. Something like that. So, nothing crazy going on here. I'm just going to integrate the function from x equals 0 to x equals root 6. That's how we find the area. Come on, give me a nice x in the numerator. And this might look a little scary at first because we've got a rational function, but thankfully this is an example where u sub is going to work out just fine. I'm panicked that my audio recording is going to stop again. Please, logic, please cooperate with me. U sub, right? If I let u equal x squared plus 2, the derivative of that is just 2x, which is a multiple of what's left, and so this is going to work out just great. Let u equal x squared plus 2, so du equals 2x dx, and I see I have x dx in the integrand, so I'm going to divide everything by 2 here so that I can see that x dx is half du. And now we can rewrite the integral. It's going to be 1 over u, right? That's the stuff that's u. It's 1 over u because x dx is going to get replaced with half du. So that other junk goes away, and in its place, we have half du. I'm going to pull out the half, though. So this is our integral. And then we just got to readjust the bounds. I accidentally moved my graph there a little bit, so sorry about that. We have to change the bounds, right? If x is 0, u would have to be 2. If x is root 6, u would have to be 8. So we're going to go from 2 to 8. And so this is equal to 1/2 of, now we can just evaluate the integral. Integral of 1 over u is going to be the natural log of u. And we go from 2 to 8. And so this is 1/2 times the natural log of 8 minus the natural log of 2, but a subtraction of logs is the same as taking the log of the quotient. So, if I'm going to have ln 8 minus ln 2, I can just take ln of 8 over 2, which is perhaps better known as the natural log of 4. And so there's my answer, 1/2 natural log of 4. That is the area under the curve from x equals 0 to x equals root 6. And root 6 is, somewhere between 2 and 3. So I don't know, something like that. All right, I'm satisfied. 1/2 natural log of 4. Moving on to part B. Interesting question. If the line x equals k divides our region R into 2 regions of equal area. By the way, I'm so self-conscious about how bad this graph might be. I gotta not dwell on it. If the line x equals k divides R into 2 regions of equal area, because something about this just doesn't look right to me. But, I don't think it's in an important way. Like, this answer is fine, but this graph, if the line, sorry, I'll let it go. If the line x equals k divides R into 2 regions of equal area, what's the value of k? Now remember, R is our region from above, so we're still going from 0 to root 6. So, this is cool. All we have to say then is if I were to integrate, well, I think we could make this easy. I don't necessarily have to set up the integrals. We could pick up from like here, because what we're trying to find is like where we have to split the bounds so that we cut the areas in half. But that's not going to change the integrand and, what the integral ends up being. So I'm just going to take this step, 1/2 natural log of u. If I integrate this from 2 to k, because I'm splitting this up at x equals k, that should be the same as if I were to go for the rest of the region. So if I were to go from k to root 6, except k is a bound in terms of x, not in terms of u. So we could, let's just replace u with the x stuff, just to make this perhaps easier. So u was x squared plus 2. So I'm going to put this back in terms of x because k is a thing in terms of x. So I want this whole thing to be in terms of x. X squared plus 2. X squared plus 2. And then 2 should go back to 0 because that's the lower bound in terms of x. And same thing over here. It's going to go from k to root 6. Root 6 is the upper bound in terms of x. X squared plus 2. Yeah, that looks good. Of course, we can cancel out the factors of 1/2, and we can try plugging this stuff in. So natural log of k squared plus 2, I'm just plugging k in, minus the natural log of 2 has to equal the natural log of 8, plugging in the square root of 6, minus the natural log of k. Not k, whoops, that's a little too simple. K squared plus 2. Okay, so this doesn't look so bad. I'll add natural log of k squared plus 2 to both sides. So I've got 2 natural log of k squared plus 2. And then let's add the ln of 2 over. So natural log of 8 plus the natural log of 2. And now I feel like I'm forgetting my log rules. Is it the natural log of a product is the sum of the logs of the factors? Yes, I believe that's what it is. So this would be the same as having the natural log of 8 times 2. So 16. Then that's how it works. And on the other side, I've got 2 ln of k squared plus 2. Okay, now let's Let's exponentiate everything, right? Let's do that. So I'm going to raise the left. I'm going to put it in the exponent of e. And the right, I'm going to put it in the exponent of e. That's going to give me e. Well, let's rewrite this one a little bit. So on the left, I've got e to the ln of k squared plus 2 squared. That's accounting for this factor of 2. And then on the right, e to the ln of 16 is just 16. And so then I'm going to have e to the ln, that cancels out. And so I'm going to be left with k squared plus 2 squared equals 16. So if I take the square root of both sides, I got plus or minus 4. So, just a square root on both sides here, plus or minus 4. So k squared, and I still got a k squared also, damn. K squared equals negative 2 plus or minus 4. K, obviously, since we're splitting the region R in 2 halves, K has to be within those bounds, 0 to root 6. So I don't have to worry about negative things here, but let me not eliminate any solutions just yet. So for sure I'm not going to have a negative here, negative 2 minus 4, because I can't take a square root of a negative. So it's going to be negative 2 plus 4, which is positive 2. Cool. And then take the square root of this, both sides. I need the positive solution because k is between 0 and root 6, and it's got to be root 2. Cool. I like seeing root 2 pop up. So, what's the value of k? It's root 2. That is my final answer. I could plug it in and double check, but I'm not gonna. I'm gonna move on to question C, and I'm gonna go wipe my nose. All right, I hope I didn't go through all the algebra there at the end too quick. It's amazing, you talk about some algebra in a video. As soon as some algebra pops up, it can make a video take so much longer because, I want to explain every step. I don't want to just magically poof, go to the end of the problem. Anyways, letter C, we're almost there. Is this the last letter in this problem? Yes, it is. All right. I can taste it. We're almost done. What's the average value of the same function we've been working with on the interval from 0 to root 6? So this is easy. We just need to integrate our function over the whole interval, which we already did, and then divide by the length of the interval. The answer here is that we need to integrate the function over the whole interval. That's like adding up all of the function's values. X over x squared plus 2 dx. And then we need to divide by the length of the interval, divide by root 6. Man, all of my work is going to be wrong if I integrated wrong in the first step, but there's no way that I did that. So I'm just going to snag our integral from the top here. Because, we went from 0 to root 6, which once we do u sub 0 to 6 became 2 to 8, which is this. It was 1/2 natural log of 4. Just double checking here, because I don't want to use this if it's wrong. I don't want to use it in another answer. 1/2 natural log of 8 minus natural log of 2, so natural log of 4. Yeah, this was the integral, same function, from 0 to root 6. Yep. I'm comfortable using it, half natural log 4. So this is half natural log of 4. Seems strangely easy, but whatever. Divided by the square root of 6. And so if I want to rationalize my denominator, that's going to give me root 6 times the natural log of 4 divided by 12, right? Because root 6 times root 6 is 6, and then I'm just moving the half to the denominator, so that becomes 12. So root 6 natural log of 4. Yeah, I think that's it. That is my final answer. It's not beautiful, but it is what it is, and there's no simplification that I can do there that I can see, so I'm leaving it as it is. Let's move on. Question 6. I can't believe it. My technology hasn't screwed up yet. Let's finish this off. Let f be a differentiable function defined for all real numbers x with the following properties. Oh boy, its derivative is that. Okay, so then f is a cubic because its derivative is a quadratic. Part 2, we are given a couple values for the derivative and then the second derivative. And the integral from 1 to 2 is 18. Oh man, we got to find the function. Okay. Find the function. Well, let's just start by integrating f prime, right? Let's just integrate f prime. If we integrate f prime, we are going to get a is going to hang out, but it's got to get divided by 3 because x squared becomes x cubed. B is going to hang out, but it's got to get divided by 2 because x becomes x squared. And then we need an arbitrary constant. Okay. And then I guess we'll have to use the integral in order to find what c is. Now let's see about finding a and b. We got to find a and b. To find a and b, well, those are two unknowns. These will give us two equations, so that should be easy. Let's take the derivative and plug in 1 and set it equal to 6. 1 squared is 1, so I'm just going to have a plus b equals 6. I'm just plugging in 1 to the derivative. And then let's find what the second derivative is so that we can plug 1 into that and set that equal to 18. I like this problem. It's cute. The second derivative is going to be 2a times x plus b. Okay, so that's nice. Let's plug in 1, set it equal to 18. That's going to give us that 2a plus b is equal to 18. Now let's do elimination. I'll subtract this equation from this equation. That's going to leave us with a equals 12. Just subtracting this whole thing from this whole thing. Cool. So that means that b has to equal -6, right? If a equals 12, plug it into this guy, and that means b equals -6. And yeah, let's just plug that in here, make sure that's true. 24 plus -6 is 18. Yep, looks good. Okay, so that means here a over 3 is 12 over 3, so that's just 4. And b over 2 is -6 over 2, so that's just -3. Now we can integrate this from 1 to 2, because this is f of x. Let's integrate it from 1 to 2, set it equal to 18, and solve for c. Yeah, cool. Let me start doing this in another color just to make my work look a little neater. And get started here. We're integrating 4x cubed. Remember, this is f of x, so make sure you're integrating the right thing. That is f of x minus 3x squared plus c dx. We want to go from 1 to 2 because we know that equals 18. All right. Yeah, and just to make my work, more clear perhaps, we integrate f prime. That's what gives us f of x. All right, so integrating over here, we're going to have x to the 4th, divide by a 4th, which or divide by 4, which cancels out that factor of 4. And then minus x cubed, isn't that nice, how nice this works out, plus cx from 1 to 2 equals 18. Plug in chug and we'll solve for 18. So let's plug in 2 first. That's going to give us 16 minus 8 plus 2c. And then minus, plug in 1, which gives us 1 minus 1 plus c. So just c equals 18. 2c minus c is just c. 16 minus 8 is 8. And then equals 18, and so c equals 10. All right, just double check that arithmetic. 16 minus 8 is 8. 2c minus c, yep. Ooh, almost made a mistake. Almost got me. No, never mind. I didn't make a mistake. For a second, I thought I had a little sign error, but this all looks good. Yeah, we subtract this stuff when we plug in 1, and the, CX is still positive, so everything looks good there. Okay, so C equals 10, so final answer up here. What is C? It's 10. That's what f of x is. Show my work. That's all my work. That's my answer to... This doesn't say 6 part A. I think that's the end of the exam. It's done. Oh my gosh. All right. Wow, that was an ordeal. That was way more draining than I expected. I got sick. It took multiple days. My gosh. Okay. I'm going to go through and grade my work, and I'll come back and tell you how I did. All right, I've done all the grading aside from the final calculation here. I got 41 multiple choice questions correct. Of the 4 that I didn't get right, I only answered 2 of them, so I subtract a 4th times those 2 I got wrong. That's 41 minus a half, and I just rounded down to 40 points. For the free response questions, this is how I saw them being graded based on the criteria provided in this document. 9 out of 9 on the 1st, 2nd, 5th, and 6th. I lost a few points on question 3. On question 4, all my math was right. I don't know if they would have taken a point off for this, but I took a point off for not fully simplifying, where we had half natural log of a 4th. Could have rewritten that as natural log times the square root of 4, because a factor can be brought in as a power, and of course that would be the natural log of 2. So I took a point off for that. Free response total ends up being 50. Now for the composite score, we got to do 200 times the multiple choice score, which was 40. So 200 times 40, and that is going to be 8,000. I'm not sure why this 200 is here. If you look at these composite score ranges, 8,000 seems a little big. I think we'll just not multiply it by anything. Let's just leave it as 40. 40 times 1. Ignore that 200. I don't know what that's doing there. So weighted multiple choice score is 40 plus the free response score of 50 equals a composite score of 90. And where does that put us, folks? Bam! AP grade of 5. And I divided my score by like a factor of 200 here. It's still got a 5, so that's what I'm talking about. About in the mid-range of the grade 5 there, so yeah, not so bad. Felt like that was a pretty easy test, even though it wore on my health apparently, and took quite a while for me to try to explain everything in a somewhat casual manner, but I hope it was helpful for anyone watching this and studying. If you go down to some of the stats they provide us here, looks like about 17.8% of the test takers got an AP grade 5 on this 1988 AP Calc exam. So pretty cool piece of history, this exam. It's fun to be able to do it, and I hope you didn't deprive yourself of the opportunity. So let me know in the comments, how did you do on this exam? What were your favorite questions? Maybe your least favorite questions? I've got to practice some of those volume problems apparently, but that's where I'll wrap it up. I hope you liked this video. Let me know if you'd like to see more videos like this, taking on a whole exam of some sort. I thought it was pretty fun. Yeah, hope you liked it. Hope it was helpful. And I'll see you next time. I'm gonna go blow my nose.